Again, it's a red stick.
What is going on, guys? Welcome to this special video here. I thought about the algorithms and data structures tutorial series a little bit, and I figured that it might be a little bit more effective if I compile all the videos into one big video, all the 23 parts into one big video, because a lot of people lose track once they watch a tutorial series. They stop after video 5 or even after video 2. So what I thought is, if some of you guys have missed out on the opportunity to watch the algorithms and data structures tutorial series and you would like to watch it in a whole video, in a whole 4-hour, 5-hour course, I'm not sure how long this is, but if you want to watch it in one video, I wanted to give you the opportunity to do that, and this is what I did in this video here. So it's a long video course in algorithms and data structures from scratch. And the reason I make this special intro here is because the videos are actually the same. So the videos are actually the exact same content that you have in the series. And because of that, I wanted to give you some context before that, because a lot of times in the videos I'm going to say stuff like in the next video or in the future video or in the last video or in the first video. I'm going to mention separate videos. What I mean by that is actually in this particular video, just earlier in the video or later in the video, because these are all the videos compiled into one big video course. So don't be confused by that. Also, because they're individual episodes, sometimes similar sentences are going to occur that might not make a lot of sense, but the content is the same, the content is well structured. So I hope you can enjoy this, and I hope you learned something, and let's get right into it. So let's talk a little bit about algorithms and data structures and about this tutorial series. And the first question we're going to cover is why you should care learning about this. Why should you learn about algorithms and data structures? Why is this important? And I'm going to give you a very straightforward reason, a very good reason to learn these things, even if you're not interested in them. And this is because most interesting companies, most tech companies that you want to work for are going to give you questions or problems based on algorithms and data structures in job interviews. So whenever you apply for Google, whenever you apply for Facebook, whenever you apply for any big tech corporation, Microsoft, they're going to give you a question in your job interview. And this question is most likely to be based on or will most likely be based on algorithms and data structures. So this is a very practical reason to learn it, but I'm also going to give you a bunch of reasons why it's important in general. Now, it doesn't matter in which field, in which subfield you want to go. If you want to be an ethical hacker, if you want to be a cybersecurity expert, if you want to be a computer networking expert, if you want to be a programmer, machine learning engineer, whatever you want to be in computer science, you will need algorithms and data structures, and you will definitely benefit of the knowledge here. In ethical hacking, in computer networking, in computer security, you're going to need to understand hashing and encryption and algorithm and runtime complexity of brute force and dictionary attacks and all that. You're going to need to have a basic understanding, a fundamental understanding of what an algorithm is, what runtime complexity is, what different data structures are, just because you're going to encounter them all over in the field of computer science. And it's the same, of course, for programmers. Whenever you're working on an application, you will have real life problems to solve, and these problems are actual problems, right? And you need to solve them with algorithms, and you can make up these algorithms from your head, but then you don't know, is this algorithm efficient? Is it not efficient? What's the runtime complexity? Is this something that can scale? Is this something that will break every computer or will take forever if I run this? So you will need to understand at least the basics of algorithms and data structures to be a good programmer, because everyone can write code that solves the problem, but not everyone can write intelligent code. And just knowing a programming language, everyone can learn a programming language. A programming language is just a tool. If you know Python, Java, C++, that's a tool for implementing algorithms, for solving problems. And if you're a programmer, you're not someone who knows a language. You are someone who has to solve problems, and you don't solve problems with Python, you solve them with algorithms that you implement in Python, for example. So this is why you need to learn about algorithms and data structures. It's one of the most fundamental fields, and it's needed everywhere. No matter where you go in computer science, you will need algorithms and data structures. Now, I hope I was able to convince you that it's a good idea to learn about algorithms and data structures. So let us get to the second point, which is the topics and the structure of the series. What can you expect from this tutorial series? And when it comes to structure, I really value flexibility in this particular case, because I'm not interested in designing a curriculum or a schedule that tells you first episode is this, second episode is this, third episode is this. and so on. I'm more interested in having a basic idea of how I'm going to structure the content. So I know first we're going to do the basics. What are algorithms? What are data structures, runtime complexity, and so on. Then the basic data structures and so on. We're not going to start with P&NP problems if you don't know anything about algorithms in general. But we're going to keep it flexible. So I'm not going to have a static structure that has to be followed no matter what. We're going to start with some basics. We're going to talk about some data structures, but if I think in the middle of the series, hey, I want to add this topic as well, I'm just going to add it without caring too much about the static structure that I have in my head. So this is just one thing that you should know. It's going to be very flexible, and the topics are going to be mainly about algorithms in general at first, runtime complexity, how to calculate them, or how to calculate it, different data structures, lists, linked lists, binary trees, and so on. We're going to cover all the data structures that are important. We're going to cover all the algorithmic complexities that are important. We're going to make a lot of, or talk a lot about examples of algorithms like sorting, searching, minimal spanning tree. We're going to talk a little bit about graph theory as well. And this is basically what we're going to do. Later on, depending on how the series goes and how much you like it, we're also going to go into more advanced topics like dynamic programming or NP problems, NP complete problems, and so on. If this series is liked by you, if you like it, I'm going to make more content, more advanced content. If you say, no, it's not that interesting, if it doesn't get a lot of views and a lot of likes from you, we're going to stop at the intermediate stage. So we're going to cover the data structures, the algorithms, the complexity, and so on. If you like it, again, we're going to go into more advanced topics as well. So this is the structure of this series, very flexible, and depending on your feedback, we're going to do more content, more complicated content, more advanced content, and if you don't like it, we're going to keep it at the basics. Now, one more thing that you should know about this tutorial series is that it's going to be more focused on explaining things simply and intuitively instead of focusing too much on rigorous scientific definitions. So we're not going to define everything scientifically accurate, which does not mean that we're going to define it in a wrong way or only scratch the surface. We're going to go deep into algorithms, but not everything needs to be defined in a mathematical, scientifically accurate way. So we're going to focus more on you understanding the concepts of linear time, of logarithmic time, of binary trees, and so on, instead of always writing down the textbook definition of a binary tree, the textbook definition of this and that. Sometimes we're going to do it when I think it's useful, when I think it's necessary. We're going to also cover scientific, mathematical definitions, but for the most part, we're going to focus on intuitive explanations of how things work and not always going to confuse you with mathematical jibber jabber or any nonsense. It's actually not nonsense, but I'm not going to make it extra complicated for you. I'm going to explain it simply, and maybe we're going to add some scientific definitions afterwards so that you're not getting confused, because I know from my own experience that oftentimes when you learn about algorithmic complexity, it's very confusing what the individual things mean. So I'm going to try to confuse you as little as possible, but at the same time give you as much knowledge and scientific accuracy as possible. So we're going to try to find the perfect balance here. Now, a lot of you guys will probably be asking right now, what are the prerequisites for this series? What do I need to already know? What skills do I already need to have before starting with this tutorial series? And yes, there are prerequisites, but they're not too big. So what you need is a basic high school level understanding of math. You don't need complex calculus. You don't need complex algebra, probability theory, or anything like that. You just should have a basic understanding of high school level math. So knowing what the logarithm is, knowing what exponential growth is, knowing what functions are, maybe knowing what derivatives are, how to take the derivative. I don't know if we're going to need that for sure, but you should just have a basic understanding of how to deal with numbers and basic high school level algebra, essentially. This is one thing, and the second thing is you should have some basic coding skills. They don't need to be in Python, Java, or any specific language, but you should know your way around loops. You should know what conditions are, if-else statements. You should know what functions are. You don't need to know any advanced object-oriented programming or machine learning stuff, just basics of programming so that you can understand pseudocode. We're going to talk about pseudocode in this tutorial series separately, but you should know basic programming concepts, loops, if statements, functions, return values, all of that, so that you can follow along with pseudocode. These are the two things: high school level maths and basic coding skills. Now, last but not least, for today's video, I'm going to announce the book or the book series on algorithms and data structures. Right now, if you're watching this as one of the first viewers, you're probably not going to be able to buy it because it's not released yet. I have started working on it, but it's still, the work is still in progress, so it's not online, it's not available. But once it's available, you will be able to find it at neural9.com/books, where you can also find other books I've written in the past. And if you want to take it seriously, you don't need to buy this book, but if you want to take it seriously, you can buy this book to supplement this tutorial series with the perfect literature for this tutorial series. So if you want to take it seriously and you want to spend some money, you can go and buy the book on Amazon. Once it's out there, you'll find it, as I said, on neural9.com/books. And there you will be able to follow along in a structured way. So this tutorial series, as I said, is going to be more flexible. The book is going to be rigorously structured from A to Z. So you're going to have a perfect structure on how to learn algorithms and data structures. And it's going to be the perfect book to supplement this tutorial series if you want to do it. As I said, you don't need to, but if you want to take it seriously, you might consider this. Also, at this link, you're going to find the Python Bible series. So if you want to catch up on some Python skills, if you want to learn Python programming, you can check out neural9.com/books and buy the Python Bible series there to learn Python from scratch. It goes from beginner, intermediate, data science, machine learning, finance, neural networks, and computer vision are the 7 topics covered in the Python Bible series. So if you want to catch up on some Python skills, you can check out neural9.com/books as well. Because in this tutorial series, even though it's focused on theory and algorithms, we will do some code probably to show you some practical coding examples, some algorithms in action in real life, or not real life, but in real code. At least we're going to see how algorithms work, and maybe we'll choose Python. Probably we're going to choose Python as a language for that. So if you want to catch up on some Python skills, check out neural9.com/books. So let's start by tackling the most fundamental question first, which is what is an algorithm? And I'm not going to bore you here with the scientific definition. I'm going to give you a very intuitive and simple definition, which is it is a set of instructions used to solve a problem. Now, problem is always a very interesting term. Problem essentially means task. So whatever you want to do, sorting a list or finding the shortest path from A to B, or finding the minimum spanning tree of a graph, finding the maximum element of a list, it's always called a problem. It's just a goal, a task that you want to achieve, and the set of instructions you need to do so is called an algorithm. So an algorithm is not necessarily limited to computers, because as a human, think about it. Let's say you want to cook something at home because you're hungry. What do? You go online, you download an algorithm called a cooking recipe, and then you follow the set of instructions in order to solve the problem of cooking a meal. That's essentially what you do as a human, and a computer has also a set of instructions for solving a problem. Of course, in this series, we're going to focus on computers, but essentially it's the same, because when a computer uses a certain set of instructions to solve the problem of sorting a list, for example, you can use the same instructions as a human to sort the list in an efficient way. So if you have 1,000 elements or 10,000 elements and I want you to sort them, you can also use merge sort, which we're going to talk about in the future what that is. You can also use the efficient sorting algorithm of merge sort to sort this list, even though you're not a computer. So it's not necessarily limited to a computer, but we're going to talk in the context of computers here. So let's get an example here of sorting a list. Let's say you have a bunch of numbers here. These are the slots for the numbers. And we have the numbers 9, 3, 4, 5, 6, 2, 1. And now what we want to do is we want to end up with a sorted list. As a human, it's very easy to see what the sorted list would be. It's just 1, 2, 3, 4, 5, 6, and 9. That's the sorted list that you want to end up with. But a computer doesn't have the kind of big picture understanding, or cannot just look at the whole picture of this list here and say, okay, I know how to sort it. I have the intuitive feeling. A computer doesn't have intuition, at least yet. At this point in time, it doesn't have intuition, so it has to use a static set of instructions in order to solve the problem of sorting a list. So what we could do here, for example, is you could just go ahead and tell the computer, go through the whole list and find the smallest element. So start with 9. 9 is the smallest element up until now. 3 is smaller than 9. So 3 is the smallest element right now. Then 4 is larger than 3. So ignore it. 5, same. 6, same. 2 is smaller than 3, less than 3. So 2 is the minimum. And then you go for 1. Okay, 1 is the minimum. So you end up with 1 as the minimum. What you do is you swap the position with the first element where it belongs. So you have 1, 3, 4, 5, 6, 2, and 9. This is the first step. Then what you do is you ignore the first element and you do the same thing for the rest of the list. So you go 3, 4, 5, 6, 2, new minimum, 9, still new minimum is 2. So what you do is you take 2 and swap it with the second position here. So you end up with 1, 2, 4, 5, 6, 3, and 9. Then you do the same thing with 3 and third position and so on. This is what you do until the list is sorted. And this kind of sorting algorithm is called selection sort. Again, I'm going to talk about sorting algorithms in a specific episode in the future. But for now, you need to know that there is an algorithm called selection sort, which essentially just picks the smallest number, puts it in the first position, picks the second smallest number, puts it in the second position, and so on until the list is sorted. This is one way, one algorithm that you can use to solve the problem of sorting a list. Now, it's not the most efficient one, and that is what I'm trying to make, this is the point that I'm trying to make here, that there are different algorithms that can solve the same problem with a different efficiency. And we're going to talk about what efficiency and good or bad algorithm actually means in one of the future episodes about runtime complexity. But for now, you need to know that there are different algorithms that work in a different way and can solve the same problem in a different efficiency, with a different runtime complexity. So the same problem does not always have the same runtime complexity. You can use a different set of instructions to solve the problem. And this is what you need to know for now, that it's important to find the algorithm that solves the problem with the best efficiency. So now let us get to pseudocode, and pseudocode is essentially just a way to put down the instructions of an algorithm, the set of instructions, into code that is not limited to a particular syntax. So pseudocode is not Python code, even though it's very similar to Python, or looks very similar to Python. It's not Java code, it's not C++ code, it's not even a unified pseudocode syntax, because people write pseudocode in different ways. It's just a logical explanation of an algorithm. You write down an algorithm in a code that may look like Python code, may look like Java code, but it's not a particular syntax that is used here. So, for example, let me give you an example, and you should be familiar with basic coding. As I said in the first video, you should know what a loop is, you should know what an array is, what a function is, and so on. But what you can do, for example, is you can say for x equals 0 to 10. This would be one way to write down a for loop that goes from 0 to 10. But you could also write it down as for x equals 0 until x is larger than 10, or larger or equal to 10, whatever it is. You can also write it down in your language. For is a pretty unique keyword that you should probably be using, but you don't have to use until. You can use the word in your language if you want. So pseudocode is not limited to a language or to a particular syntax. Now, to get an example here, let's just start by defining a list of numbers, but this time we don't want to sort this list, but we want to find the biggest element, the largest element of that list. So let's say we have 2, 5, 1, 8, 9, and 6. These are the values, and what we want to do now is we want to find the largest element. In this case, of course, this is 9. But we want to write an algorithm in pseudocode that finds the largest element. So what we could be doing is we could just go ahead and say a equals, and then you can just write list of numbers or something, or you can actually write down the numbers, doesn't matter, because the focus is not on creating a list, the focus is on finding the maximum element. So now you could go ahead and say, or actually we should use a colon here as well, max element is a index 0. Okay, this is a very ugly a index 0, because that essentially means we take the first element. It doesn't make sense to set it to 0 or to 1000 or to minus 999. Just pick the first element, because you're not going to find an element as your max element that is not on the list. So you're definitely going to succeed if you take the first element as the initial maximum element. So you just take index 0 here, and then you can just go ahead and say for each number in A. You can write it down like that. There's no problem with that. It's pseudocode. For each number in A, if number is larger than max element, then you can say if number is larger than max element, we just say max element equals number. That's a simple algorithm that is always going to find the largest element, sorry. So let's go through it. You create a list of numbers. We have a list of numbers here. Maximum element would be 2. Okay, let's save it. And then what you do is, okay, you say for each number in A, if the number is larger than max element, set the new max element to the number. So what you do is you compare 2 with 2. Okay, it's fine. It's the same number, so we don't do anything. You compare 5 to 2, you see, okay, 5 is larger than 2, so what you do is you say 5 is the new maximum, then you go to 1, ignore 1, 8, okay, 8 is bigger than 5, so you choose 8, then you go to 9, 9 is larger than 8, so you choose 9, then 6, you ignore 6, and you end up with 9 as the maximum element. This is one algorithm that you can use to find the maximum number of a list, and this is the one pseudocode that you could write for that. Now the example is not very complex, but I wanted to show you what pseudocode looks like. It is basically just writing down in a code-like way what you're doing. For example, look at this line here, for each number in A. I mean, you can write it like that in some languages, but it's just explaining what you're doing. It's not, you don't have to care about a certain syntax. You just want to make it understandable what you're doing. You're looking for each number in A, and for each number, you're comparing the number with the maximum element. And this is essentially what pseudocode looks like. We're going to look at a lot of pseudocode in the future episodes. So this is a brief introduction into pseudocode. So let us talk about the first question, which is what is a data structure? And a data structure is essentially just a way or a format for accessing, storing, managing, organizing, or as the name suggests, structuring data or information. For example, from programming, you already know what an array is. An array is just a collection that has a fixed size. For example, here we have an array of size 6 and it equals 6. And this array has certain elements, for example, A, B, C, D, E, and F. And this array, the array is a data structure. So the array, okay, ugly A again, array data structure. Now, this data structure has certain advantages and disadvantages. For example, an advantage is that I can access each element without going through all the other elements. So what I can do in order to access this element here is I just say I want to access index 4, I think it is 0, 1, 2, 3, 4, 5. Yes, I just say I want to access index 4 and I can access E without a problem. I don't need to go through A, B, C, D to reach E. I can just go ahead and say I want index 4 and I get it directly. This is called I can access E in constant time. We're going to talk about runtime complexity in a future episode, as I already said. But this would be an example of constant time. I just say I want to get to index 4 and I get to index 4. It's not hard. I don't have to iterate over all the elements that come before E. A disadvantage here would be that I'm not able to just go ahead and append a new element and increase the size of the list. I'm not just able to say, okay, let's change n to 7 here and let's increase the size of the array. It's not possible with an ordinary array. I cannot just say, okay, I have a new index here and let me enter a G here. This is not possible with an ordinary array. And this is the reason why we have different data structures. Depending on what you need, on what you prefer, you have to choose a certain data structure that fits your goals. And in this video, I'm not going to talk too much about the different data structures. We're not going to explain the different data structures because the data structures will be explained in detail in separate videos. But I'm going to introduce to you today the concept of a linked list, just so you see, roughly speaking, we're going to talk about linked lists in detail as well. But today I'm going to just give you a rough explanation of what a linked list is so that you can see why we use different data structures. And what a linked list essentially is, it's just a list that's composed of nodes, and the nodes have values. For example, this could be A, and each node has a pointer to the next node. So again, I'm not going to explain in too much detail. Just roughly speaking, you have a value and a pointer to a next value, or to a next node that again contains a value and points to a next node. And this contains a value, points to a next node. So having that structure allows you, of course, and the last element points just to nothing, to null, so to say. So this structure allows you to have a dynamic size. So what you do here in order to add a new element is you just say, okay, remove this null pointer here and just let it point to another node. You just have to create another node, and this node then points to null, of course. I think the camera is maybe blocking the view here. A, B, C, D, E, and then to null. It's very easy to just remove elements or insert new elements. It's not a static size here. You can just go ahead and add new elements. You don't have to add them in the end. You can also go ahead and just say, okay, I want to have a Z here, and this Z points to A. It's not a problem. You can also just go ahead and enter a new element, I don't know, X here, and let B point to X and X point to C, whatever you want to do. And then of course you have to remove this connection here. And essentially this is what you can do with a linked list. So you have the benefit of a dynamic sizing. However, if you want to access the element C, for example, it's not that easy. You cannot just go ahead and say, I want to access this element here with index 0, 1, 2, 3, 4. It's not just as simple as it is with an array. And that's the disadvantage of a linked list, because what you would have to do here is you would have to go, if you want to access index 4, what you do is you start here and you count, okay, this is index 0, then go one step further. This is index 1, go one step further. This is index 2, 3, and 4. Now we're here. So in order to access index number 4, you have to go through 0, 1, 2, and 3 in order to access 4. This is the disadvantage of a linked list. Again, the focus here is not on linked lists or arrays. The focus is on understanding why we need different data structures, why it's not enough to just have the same data structure over and over again. For example, if you want to search, if you want to have an efficient search, you want to have a binary search tree, for example. You have different data structures for different purposes. Now you might be asking, where is the interconnection between algorithms and data structures? Why are these topics always taught together? Why are they not taught separately? Why do we not have a tutorial series on algorithms and then one on data structures separately? Why are they interconnected? And the answer is because you need both of those in both ways. So data structures need algorithms and algorithms use data structures. It's just they are deeply interconnected. So for example, let's take the example of a linked list. Whatever you do with a linked list, you have some values here. A points to B and B points to C and so on. Whatever you want to do here, this demands algorithms. So if you want to find an element, if you want to access an element, if you want to add an element, these operations are not just adding. It's not just adding a new element, inserting a new element. Behind the inserting a new element, there is a set of instructions, an algorithm essentially. So if I decide that I want to create a new node here, X, and I want to add it right in here, what do? I first of all delete the connection from B to C. I let B point to X and I let X point to C. Again, don't get too confused about linked lists. We're not teaching linked lists yet. I'm just showing you that algorithms are necessary here, because inserting a new element into a linked list needs a set of instructions that is different from a set of instructions that is needed for a binary tree or an array. So it's a very different thing adding an element to a linked list than adding an element to an array. And it's the same for finding an element in a linked list, as we already talked about it. You need to go through all the nodes until you reach a node. So the algorithm is next, count up, next, increase the counter, next, increase the counter, and so on. Whereas in an array, you just go ahead and say, access this memory location. So it's a different runtime complexity. It's a different efficiency accessing an element or adding an element, removing an element from an array than it is from a binary tree, than it is from a linked list. This is this way. So data structures need algorithms, but algorithms also need data structures. If you want to solve a problem, you will need to make use of data structures. And depending on the problem, you're going to need different data structures. Sometimes you might have a queue of items that need to be processed by an algorithm, so you might use a stack. Again, if you don't know what a stack is, don't get confused. We're not talking about the data structures yet, but the stack is essentially, you add items, you get items in a queue sort of way, in a queue-like way. So you just push some items onto the stack, then you pop them out of the stack, and then you process them. And if you have a certain algorithm that needs to do to process elements in that way, in a so-called last in, first out, or a first in, first out kind of way. You're going to use a stack as a data structure to help, as a data structure that your algorithm uses to solve a problem. So algorithms need to make use of data structures, and data structures, all the operations inside of data structures, are based on algorithm, on a set of instructions. So let's start by talking about efficiency, because efficiency is a very vague term and it's constantly used when it comes to algorithms. For example, if we analyze an algorithm, we always want to know, is this efficient? When we analyze two algorithms, we want to know which one is more efficient, but we need to define efficiency in the first place. What does that mean? Because everyone can define different metrics for efficiency. So for example, one possible metric would be the memory space. It might not be the first thing that comes to mind, but the memory space is definitely something that's important. Let's say we solve a problem in 10 seconds. This is just an imaginary example here, but we solve a problem in 10 seconds, but it takes 10 terabytes of space to solve the problem for some reason. Then we have another algorithm that solves the problem in 10 minutes and only takes 20 gigabytes. If this is the algorithm, or these are the two algorithms, if you look at speed, you're going to pick the 10-second algorithm. If you're going to look at space, you're going to pick the 20 gigabyte algorithm here. So it is important what kind of metric you choose, because another metric, of course, would be the runtime, which is essentially the time it takes to solve a problem, to finish a task. In this case, this one would win, but if we look at memory space, this one would win. Also, you can add some additional metrics, like, for example, problem-specific metrics. If you're solving the problem of sorting a list, you could say the number of comparisons, for example, number of comparisons made, or number of swaps. So for example, you could say when you're dealing with sorting algorithms, you could say, okay, I really don't care about the number of comparisons. I'm not going to talk about that when I talk about efficiency, but I really care about the number of swaps I did. So if I compare numbers, it doesn't matter, but if I swap them, this is an operation that I want to look at. It doesn't make sense, but you could do that. So the metric for efficiency is whatever you define it to be. In this tutorial series, we're mainly going to look at runtime as a metric. We're going to look at runtime complexity in particular, because this is what we're going to define in this video even further. But as you're going to see, runtime is also a very vague term in the beginning. Now, because of that, let us talk about the question of what runtime actually is. And let's go ahead with the naive understanding of runtime is just the amount of time units, seconds, minutes, whatever it takes to solve a problem using an algorithm. And essentially, this definition is not wrong, but it's not the one that we're going to use for this tutorial series, because it will get us into some problems, and we're going to look at what these problems are. Let's say, for example, we have a computer A here, and we have a computer B here, and then we have an algorithm X that solves a problem in 10 seconds, and then we have the algorithm Y that solves the problem in, 2 minutes, which is essentially just 120 seconds. Now, looking at this and looking at the definition of runtime that we just defined, is X actually faster or more efficient than Y? Yes, of course it is, because what do we have here? We have 10 seconds of runtime and we have 120 seconds of runtime. And I think you can see that this is a problem here, because we're running two different algorithms on the same problem, but on two different machines, and we don't know anything about these machines. For example, B could be a machine of the year, 1990, for example, and A could be a machine from 2020, and it could have a very high-end hardware, and it could be a very, very efficient machine, whereas B is a very old and laggy computer. So what would be a method to counteract this? Well, you could just go ahead and run algorithm Y on machine A as well. So you essentially run both algorithms on the same machine instead of using two different machines. So what you could do is you could just go ahead and say X runs on A in 10 seconds, or solves the problem in 10 seconds, and Y solves the problem in, 8 seconds. Now you can see, okay, Y is better or more efficient than X, but is this true as well? Because sometimes this might be the case. These numbers are not that different. 8 seconds, 10 seconds, it's not that much of a difference. So what happens if at another point of time x takes 9 seconds and y takes 10 seconds? Could happen. But the question is, like, how can we determine if that is if x is more efficient than y, or if y is more efficient than x? How can we determine that? And also, even if it was possible to do this at the same machine, what would that mean? Would that mean if I want to compare my algorithm here in Austria with your algorithm in the US or in the UK or anywhere in the world, would we have to go to the same computer to execute the algorithm to see how long it takes? Of course not, because that would be unrealistic. We cannot have one central computer where everyone goes to measure how long their algorithm takes to solve a problem. And besides that, of course, we have multiple different factors outside of our control, outside of the algorithm's control, outside of anything to do with the algorithm, that are going to influence the runtime. So for example, in one time period, your computer might lag a little bit, it might have certain tasks in the background, or multiple different factors are going to influence your runtime by 2 seconds, maybe by 2 minutes, depending on what you're doing, what algorithm you're using. So it's not realistic to use actual hardware to determine the runtime complexity or the runtime in general. So what we do is we assume a certain model, a simplified model of a computer, and this model contains 3 steps here, or 3 pillars, principles here that we're going to use here. And I'm going to explain to you why these are important. You don't have to memorize them. You just need to know why we're doing that. And the first point is we have a single CPU, a single processor, which essentially just means we don't care about multi-processing, multi-threading. We're not going to take that into account. We're just going to work with one CPU and nothing more, nothing less. This is just important so that you don't come up with the ideas, but hey, I can process multiple things in the same second, in the same time unit. This is not going to happen here. Second thing is all the data, information, whatever we do with our algorithm is going to be in the RAM, in the random access memory, which essentially means that we have a very fast access. We don't need to go into the hard drive and look for files in the system. All the data we use with our algorithms in this model is going to be in the RAM. And third, and last but not least, is going to be every access is going to take the same amount of time. So it doesn't matter if you're accessing the dataset A or the dataset B, it's going to take the same amount of access time, because we're not going to limit ourselves to hardware stuff. We're going to work on a very high level here, on a very abstract level. We're going to look at the efficiency of the logic of the algorithms. We're not going to waste our time with some hardware stuff, like maybe if we're accessing this part of the RAM, if we're accessing this part of the memory here, we're going to take a little bit longer. We're not going to care about that. We're going to care about the algorithmic logic and how efficient it is. So this is the problem. This is the model that we're going to work with in this tutorial series. Now we have a model and a framework to work with, but we still don't know what runtime actually is. We still haven't defined that yet. And in order to do that, we're going to introduce something called primitive operations. Primitive operations. And these are essentially operations that all take, if we don't define it differently, one time unit. This time unit can be whatever you want. It can be seconds, minutes, whatever it is. But all these primitive operations are going to take one time unit unless we define something else. And primitive operations are everything like assigning a value to a variable like that. So a equals 10, or if you want to write it like that, a equals 10. This is a primitive operation and takes 1 unit of time. Same goes for every kind of addition. So a equals 10 plus b, if we have b defined already, is also 1 unit of time. Now in hardware, in a low level, it would make a difference. It's not always the same. Assigning a value to another or assigning a value to a variable would take less time than assigning the result of an addition. But in this case, we define primitive operations as all these easy things to do, like adding, or also logical operators like A and B, logical and B. anything that's a primitive operation takes 1 unit of time. Also, every kind of comparison. So if I say if a is greater than 10, then, and then I open a block and do something, this line here takes 1 unit of time. Okay, so these are the primitive operations and they all take 1 unit of time. And now the runtime is nothing but the amount of primitive operations needed to solve a problem. So this is, maybe we're going to write that down. It's the amount of, and I'm not going to write it out, the amount of primitive operations needed to solve a problem. That's what it is essentially, with a particular algorithm, of course, so not in general, but the runtime of an algorithm is the amount of primitive operations needed to solve a problem. This is what we're going to look at. We're not caring about seconds because that is always going to be the same. If you have a computer that processes 1 primitive operation per hour, not going to see that, but if you have such a computer, even if it takes 10 hours, it's still 10 primitive operations that were executed. If you have a very fast computer, you might do this in 1 second or in half a second, in a millisecond, whatever it is, but you still have 10 primitive operations. So the runtime doesn't depend on the hardware, it only depends on how many things do I need to do. And why do we even need to call it primitive operations? Are there any operations that are not primitive? Are there operations that take more than 1 unit of time? And yes, they are, because we talked about pseudocode already. In pseudocode, I can write whatever I want. So I can say I have a list here, and the list is, or contains a couple of values here. And then what I can do is I can just write sort list, or sort the list. I can just make a statement like sort list, and I don't even have to define sort. I don't have to write a sort function down here that takes a list and does something. I can just write sort list, and I can say, okay, I'm using merge sort for this, and we're going to talk about sorting algorithms in a future episode, but I can use merge sort for that. It's not a problem. And if I know, okay, the runtime complexity of merge sort is n log n, I can say, okay, this line takes such and such, or so and so many primitive operations, but essentially I can write lines that have way more, or need way more steps in primitive operations than just 1 or 2 or 3. And this is why it's important, because if I have a line like this, I have a certain runtime complexity in that line itself. Whereas if I have something like creating a list and comparing values, adding values, increasing values, assigning values, it's all primitive. These are all primitive operations, but something like sort the list or find the minimum spanning tree of a graph, I can just write that out in words, but it is not a primitive operation. It's a whole procedure. It's an algorithm in and of itself. So sorting is an algorithm here, and it's not a primitive operation. This is why it's important, and that is what we're looking at. We're looking at the amount of primitive operations needed to solve a problem with a particular algorithm. Now we finally know what runtime is and what we're looking for, but there's still more problems that we can encounter here, and I'm going to show you what I mean by showing you some pseudocode. So we're now going to analyze the runtime of an algorithm here, and it's going to be a very simple one. It's not really an algorithm that solves the problem, it's just code that does something, but we're going to try to determine how many primitive operation this code executes. So now we're going to look at a practical example here. Let's say we start with a list, and this list is a list of some numbers in here. We're not going to statically define it, it's just a list of numbers. And inside of this list we have some elements, and we could say we have n elements, an amount of n elements. And what we could now do is we could go ahead and also define a variable a, and this is 0. And then we're going to run a for loop that says for each element in list, we're going to do 2 primitive operations. So for example, we could say a equals a plus 1, and we can say print some message here. Now let's assume that all these are primitive operations. So this is a primitive operation, 1 primitive operation. Actually, this means first 1 primitive operation. This is one primitive operation. We're just assigning 0 to a variable. This is a primitive operation. And this, we could also say, is a primitive operation. So essentially we have 4 primitive operations here, and this loop, obviously, if we have n elements and we iterate through the whole list, so we go for each element once, this loop is going to run n times. And essentially what you have is you have 2 primitive operations here, 2 primitive operations plus n times 2 primitive operations, because you run this loop n times and you always have 2 primitive operations in here. So essentially you would end up with a runtime here of 2 plus 2n, which is just the amount of primitive operations of this algorithm. Now, so far so good. It's very simple to understand. You just create a list, you have a counter, you increase this counter for each element, and then you print a message every time, whatever it is. It's very simple, and you always have the same amount of primitive operations. Of course, independence of n, it's not a constant number. Depending on the amount of elements, you have a different amount of operations. But now we're going to add a twist here. Actually, let's just keep these things here, but let's just remove this part of the code here, because we're going to add something to this loop here. And this is an if statement. We're going to say if the element that we're currently looking at, if this element is odd, or let's say if it's even, if this number is even, then we're going to, and you can write it like that. It's pseudocode, so essentially what this means is you're trying to find out with the modulus operator if the number is divisible by 2 without remainder. But you can write it like that. If element is even, you're just going to say a equals a plus 1 and then print the message. So the same code that we just had, but inside this if statement here. And this is again one primitive operation. This is one primitive operation. And now the checking here, if the element is even, is also a primitive operation. This loop still runs n times. And now things are getting a little bit more complex, because we're creating a list here and we don't know the elements here. The elements are going to be different every time. So maybe we have a list full of even values, maybe we have a list full of odd values, or we have a mix of the two. So the problem is, now these two steps are obviously 2 primitive operations, so we can write that down, 2 primitive operations. But then we also have this loop n times. And of course, you're going to check every time, so you definitely have n times this line, because you're going to say, you're going to always do the if statement. You're always going to check if the element is even. So you definitely have n primitive operations at least. But how many times are you going to enter the if block? And you don't know that in advance, because maybe all the elements are even. So in this case, you would enter it every single time and you would have essentially 3n. So if all the elements are even, you would have 3n, because you would run n times in 3 primitive operations. Or if none of them is even, you would only have n, because of course you will check every time, but these 2 lines are never going to get executed. So there are differences. It's not always the same amount of primitive operations. It's not always the same runtime for an algorithm. And this is why we have a distinction here, or 3 cases that we want to distinguish. And these are the best case, the average case, and the worst case. So the best case is essentially the case with the lowest runtime, with the least amount of primitive operations. So the best case is what is the fastest way, what is the least amount of primitive operations, essentially. So in this case, you would definitely have 2. There's no doubt about that. So we have 2 primitive operations, and we have definitely n times this loop, and we're always going to check. So you have n elements at least, but then, you know, all the elements are odd, because this would be the best case, because you don't have to do these 2 operations then. So you would just have 2 plus n. This would be the best case runtime. You would have 2 plus n primitive operations. Whereas the worst case would be all the elements are even. So every time I'm going to enter the if statement, and the worst case would then be, of course, 2 plus 3n, because every time it would go into this loop and execute 3 statements here. So essentially you would have 3 primitive, let's shift this to the left a little bit, 3 primitive operations n times. So 2 plus 3n. And now it comes to the average case. what is the average case? It's very hard to define the average case, which is also why it's not really used very often, because the average case needs a very accurate distribution of elements. And if we don't know that on average, or if we know, for example, that the list elements are going to be random, we can say, okay, it's going to be probably 50-50. So half the time you're going to enter the if statement, half the time you're going to not enter the if statement. And then we could say, okay, half of the time you're going to execute 3 primitive operations, and the other half of the time you're going to execute just 1 primitive operation per iteration. So you could say, if you know the distribution or the probability of the element being even or odd in the list, you can do that. But most of the time we're not going to use the average case, because the average case is not realistic unless you really know how your data is structured. So most of the time in algorithms, when we talk about the efficiency of algorithms, when we talk about the analysis of runtime complexity, we're always going to look at the worst case. The worst case is what we're interested in, because we want to know how bad can it get if we really screw up the data, if we really screw up the instance of the problem. So some sorting algorithms, of course, if you give them a sorted list, they're done. So they need, I don't know, n operations to check if the list is sorted, but that's essentially it. We don't need anything else. Whereas if it's unsorted, it's going to take n squared primitive operations. In the best case, of course, it could be interesting, but most of the time we're really interested in the worst case, because that is what tells us how bad the algorithm can get in the worst case. That's essentially it. So last but not least, let's talk about asymptotic growth, because that's the last piece of the puzzle that's missing. And this concept is essentially saying that we're not interested in small numbers, we're not interested in constants, we're interested in what's happening in the long run. So let's say we have a function depending on n, so we have f of n, and this function essentially tells us how many primitive operations do we need to perform to solve the problem or to execute the algorithm. So in the example we just had, this would be 2 plus 3n in the worst case. So this would be the function. And what we can do with these functions is we can plot them. So we can go ahead and plot a coordinate system. I'm not going to do this professionally. I'm going to make an extra video where I'm going to do this in a mathematical program. There we're going to look at all the different runtime complexities like n squared, log n, and 2 to the power of n or something like that. But essentially, you can plot all these functions, and these functions are just the runtime complexities, the runtime of the algorithms, the amount of primitive operations, independence of n. So in this case, let's just pick a different function here. Let's delete this. Let's say we pick a constant function, so a function that does not depend on n or doesn't have n as a factor. So we could say something like 10,000, which is a pretty big number, so 10,000 primitive operations. And then we would have something like g of n, and g of n would be, I don't know, 2n, for example. And now what we do is we plot these functions. So f of n would be a straight line at 10,000, at y equals 10,000 constantly. So something like that. And then we would say, here is the point 10,000. And 2 of n would be a linear function. So essentially we would, let's get the red color here. We just have a straight line that looks somewhat like that. And as you can see, what you can see here is in the first, actually 5,000, in the first 5,000 n's, for the first 5,000 values that we can input into the function here, we're going to see the blue function dominating the red function. So you could say 10,000 is bigger than 2n as long as n is less than 5,000. Obviously, because when you have 2 times 5,000, you get to 10,000, and then it's no longer dominating it. But up until this point right here, the blue function is dominating the red function. But from this point onwards, there's not a single point where this is going to happen again. And this is the concept of asymptotic growth, essentially, because we're not interested in what's happening up until a certain point. We're interested in what's happening forever. So this number doesn't have to be 5,000. It could be 50,000. It could be 5 million, 500,000. It could be 5 million. It could be 5 trillion. Whatever it is, we don't care as long as there exists a point from which on this is never going to happen again. So when we're talking about which which algorithm is more efficient, we're not looking at what's happening for a very long time. We're looking at what's happening forever, because no matter how big this number is, this span here, this range here is finite. It's a finite amount of values that we have. And for this time period here, for these inputs, okay, one function is dominating another one. But in the long run, we can see that once we reach that point, once we reach that intersection, it's never going to be the same again. So we can say in general, 2n is dominating. This is the sign for dominating. 2n is dominating 10,000. And it's actually dominating any number that you can come up with, any constant, because eventually n is going to reach half of that. So n is eventually going to reach this number divided by 2, and from this point on, 2n is going to dominate this number. So this is of course not only true for 2n and a constant, or n and a constant, this is also true for quadratic functions and for exponential functions. So the general principle here is that we do not care about the first couple of values, even if they're a trillion values. We don't care about finite amount of values. We care about what's happening in the long run. So if I have something like 3000n here, and let's say 0.1n squared, let's plot these functions here. I could say I have a very steep line like that. This would be 3000n. And then I have a very flat curve, which is 0.1n squared, something like that. Doesn't matter what this looks like. Doesn't matter how flat this one is and how steep this one is. Somewhere eventually we could go up here somewhere in a very long time. Somewhere these two lines are going to intersect, and you will see that the blue line is going to be below the red line eventually. I'm going to show you that in a separate video. One of the next videos is going to be about that. I'm going to show you the different runtime complexities, and it doesn't matter how long the blue function is going to dominate the red function here. All of this doesn't matter because there's some point somewhere here or somewhere even farther to the right where the red function is going to dominate the blue function forever. So you could say 0.1n squared is dominating 3000n, which is actually not a good thing because it means that when we have a large enough input size, n squared or 0.1n squared is going to be less efficient than 3000n. So this is very important. We don't care about small numbers. We don't care about constants because the general fact is n squared is dominating n. And it doesn't matter if you add something to it, if you say, okay, but what if I say times 5,000? What if I add a million here? What happens then? It doesn't matter. So when we're looking at asymptotic growth, when we're analyzing the efficiency of algorithms, we don't care about constants that we add. We don't care about constant factors. We care about the essential stuff like n squared dominates n, and that's enough already. So we don't care about anything else. We care about what's happening forever. And this is the concept of asymptotic growth. So the big O notation is essentially just a mathematical way of writing down which function is limiting another function. So imagine you have the function f of n here, and this function is something like 50n, and then you have g of n, and g of n is just n squared. Now, if we use a coordinate system here to plot these two functions, what you can see is that you have a pretty steep linear function, and then you also have n squared, essentially. Now, this is not n squared, actually. Something like that would be n squared. But as we saw in the last video, there will be some points, since n squared is growing way faster than n, where n squared is going to intersect with 50n, and then n squared is going to dominate 50n, obviously. Now, what we say mathematically here is that there is a point from which on n squared is going to limit 50n, which means that there is one starting index, let's call it big N or uppercase N, and this starting index, from this starting index on, we can say that for each n that is larger than the starting index, we can say that n squared is going to be larger than 50n. Now for the big O notation, we can add something more. We can say that this is even true if we have, or we can use the big O notation even if we have a constant. So essentially, if I have any constant here, and this constant could be a trillion, a million, whatever you want, just some constant of the real numbers maybe as a limitation, multiplied by that n squared, and then choosing a starting index. And if that is always true, if this inequality here is always true, then we can say that 50n is in big O of n squared. This is how you write that down. The equal sign here, don't confuse it. Essentially, if you were to treat it mathematically accurate, you would have to say 50n is an element of O of n squared, because O of n squared is essentially a set, and this set is every function that is limited by n squared. Now, limited by n squared is exactly that. It means that I can choose a constant c, multiply it with n squared, and then this here is always going to be larger than some function on the right. And this is true for infinitely many n starting at a certain uppercase n at a certain starting index. This left thing here is always going to be larger than the right one. So in this case, it's pretty obvious that n squared is going to be, or 50n is going to be in big O of n squared, but I can also do this for something like 17n squared plus, I don't know, 5n plus 30, for example. This is also in big O of n squared. Even though n squared is actually less than 17n squared, this is still true, because if I solve this, or actually not this one, but if I say 17n squared plus 5n plus 30 is always going to be less than n squared times any constant, and this is true for infinitely many n's, I can definitely, if I solve this inequality here, I can definitely find a c and a starting index n for which this is true. And this means that essentially the left term here, the left function here, is in big O of n squared. This is what this big O actually means. Now, this is not the case, for example, if I take something like, I don't know, 30, or actually not just, let's say n to the power of 3. And I say n to the power of 3 is always going to be less than n squared times any constant. This is not true, because there will be a point eventually, because what is this essentially saying? This means it's n times n squared is always going to be less than n squared times c. Now, whatever constant I choose, I can find eventually, if I go towards infinity, I can always reach an n that is going to be larger than c. And as soon as I reach that n, it's no longer going to be true. So the inequality is not going to always be true, or to be true for infinitely many values. I cannot find a c and a starting index uppercase n for which this inequality is going to be always true. Therefore, n squared is not in big O of n to the power, this is true, sorry, n to the power of 3, so n cubed is not in big O of n squared. This is not the case. In the same way, n squared, of course, is not in big O of n, and so on. So whenever you can find a constant and a starting index for which this type of inequality is always going to be true, then you can say that the left function is in big O of the right function. So it's limited, it's the upper boundary, it's limited by that function. Now we can also go ahead and do this the other way around with something called the omega notation. So it's essentially the same thing as the big O notation, just the other way around. So you're trying to find a function that is bounded below by another function. So essentially just the same thing the other way around. You have f of n, and this is some function here, I don't know. Then you have g of n, another function. And you know, we talked about if f of n is always less than g of n times a certain constant for every index n that is larger than a starting index n, and this n is going to be larger than 0, and we can also say c is larger than 0. What you can say is that essentially then, if this is the case, f of n is in big O of g of n, and now you can swap this around and you can say, okay, if f of n is always larger than g of n times a constant for all n larger than some starting index, with c and the starting index being larger than 0, greater than 0. If this is the case, you can say that f of n is bounded below by g of n, and this essentially means that f of n is in omega. Okay, this is not a very beautiful omega sign here. In omega of g of n. This is essentially just the other way around. which essentially means if you can find any C, and the C can be something like 0, 0, 0, 0, 0, 0, 0, 1, just not negative and not 0. If you can find a number that a constant that you multiply with the function or the term, so this expression here on the right, and you can find a starting index uppercase n, and for all n's larger than that index, for all n's from a certain index onwards to infinity, this inequality here is true, then you can say it's an omega of g of n. It's the same thing as the big O notation, just the other way around. And also if you can say it's both, so if, let's write it down mathematically, if f of n is in big O of g of n, and f of n is in omega of g of n, this essentially means that f of n is in theta of g of n, which essentially means that they have the same asymptotic growth. For example, you can say, what did we have? 17n squared plus 6n plus, I don't know, 25. This is in big O of n squared, for example. At the same time, 17 n squared plus 6n plus 25 is in omega of n squared, because you can find a constant so that n squared is always less than this left piece of mathematical expressions here. And this essentially means that 17n squared plus 6n plus 25 is in theta of n squared. And this obviously also means that n squared is in theta of 17n squared plus 6n plus 25. And this essentially means that they have the same asymptotic growth. So you could say they have a very similar efficiency, same asymptotic growth, runtime complexity, so to say. So what you do when you're treating algorithms essentially is when you end up with something like this is the amount of expressions, not expressions, what was it? Primitive operations that we do. You can essentially say that the runtime complexity of the algorithm is in O of n squared. You're not going to say it's in O of 17n squared or something. When you analyze an algorithm and the result is something like the primitive operations, worst case, are something like 7 steps for sure, then 12n, and then, I don't know, 24n squared and 3n to the power of 3, because you somehow calculated that, you analyze that, it essentially just boils down to the algorithm has a runtime complexity of big O of n to the power of 3. The cubic runtime complexity. That's essentially it. That's how you write it. It's also the same. You can also say it's in theta of n to the power of 3, because this doesn't give us a lot of information, because I can also say, of course, it's in big O of n to the power of 20. Wouldn't be wrong. But it's not necessarily what I'm looking for, so maybe the theta notation here is more useful. You just say it's in theta n to the power of 3, which means that that is the asymptotic growth of that runtime complexity. So now let's go through an actual example here that you might be given in college. So this is the function that we have, and we have to show that this function, that it is in big O of n squared. That is something that we need to show. This is our task right now, so let's go through it mathematically correct. What you need to do is you need to show that this thing here is less than c times n squared. C can be any number, and this is true for all n's bigger than or larger than some uppercase n. And we need to find this uppercase n here, and we need to find the c in order to prove that this is the case. So what you can do here is you can just go ahead and divide both sides by n squared. So you have 32 plus 17 divided by n plus 5 divided by n squared. And then you have has to be less than c. Now, essentially, you could go ahead and just prove it by choosing a ridiculously high c and a ridiculously high n, because it's going to be true eventually. You know, you can just go ahead and say c is 1 billion and uppercase n is 1 trillion. It's going to be true. Who cares? But we want to get a somehow not ridiculous solution. You want to have not necessarily the best solution, not necessarily the smallest possible values, but you want to have something that is reasonable, that we can work with. So what you want to do is you want to definitely find a C that is larger than these numbers on the left. So what you want to do is you want to have a C value that is going to be definitely larger than 32, because since n is going to be a positive number, we're going to have a number that is definitely going to be larger than 32. So what you can do, for example, is you can just say, okay, let's say C is 34. What I need to do then is I need to find a capital or a uppercase N here, capital N here, that is going to make sure that all the other n's that are bigger, larger than this n, are going to result in these two fractions here being less than 1. Because if these two are less than 1, I have 32 plus 1 plus 1, and this has to be less than 34 then. So I can see that 17 divided by n is going to be less than 1 when n is larger than 17. And for this one, it's the same, because if I have n is larger than 17, I'm going to have 17 squared, and 17 squared is definitely going to make this fraction here less than 1. So I essentially can say, okay, if n is larger or equal to 18, not 11, sorry, 18, and C is 34, that is the proof that this left expression here is in big O of n squared, because I can just go ahead and say, okay, 32n squared plus 17n plus 5 is always going to be less than, not C, sorry, we already calculated C, 34 times n squared for all n's that are larger or equal to 18. And this is obviously the case because we showed that it's the case by eliminating, or not eliminating, but looking at these fractions here. And the moment that I pass the number 18 for the index, I'm definitely going to have a larger product on the right side, or a larger number on the right side here. So this is definitely proven, and this is how you can prove mathematically that this left expression here is in big O of n squared. So let's start with the most desirable one, which is the constant runtime. And a constant runtime is represented visually by a horizontal line, because no matter how big the problem instance gets, I'm always going to have the same amount of steps. So for example, let's say we have a linked list. Even if you're not really familiar with a linked list, it essentially means that we have elements in a list-like structure, but to get to element number 5, we talked about this already, we need to iterate through all the elements before that. Now, it doesn't matter if the list has 1,000 elements or 5,000 elements or a quadrillion elements or just 5 elements. To access the element at position number 5 takes 5 steps. Next, 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 and I'm there. So this would be a constant runtime complexity. It would not be 1 as we see it here. It would be 5. So let me change that. Essentially means 5. So a constant runtime complexity is not growing. It's always going to be the same, and this number can be extremely high, but it's still going to be the most desirable thing. Now, in real life, you're not going to encounter a constant runtime of, I don't know, a quadrillion, so it doesn't matter. But this is usually what we hope for. This is the best case scenario. You cannot get better unless a problem is already solved, then you need 0 steps. But essentially, this is the best runtime complexity that you can have. It's essentially not growing. The growth is 0. So the next best thing that you can hope for, if you're not having constant runtime complexity, but you still want to have a very small runtime complexity, so a very, very slow growth, what you want to hope for is the logarithmic runtime complexity. And a logarithmic runtime complexity looks like that. It's the logarithmic function. And this essentially means that it's growing, but it's growing very, very slowly. It essentially means no matter how high I get, I'm going to have a very, very slow growth. Now this in this case is the logarithm of base 10, so it's growing even slower than the logarithm of base 2, for example, or the natural logarithm. But it essentially is a very, very slowly growing function. So it's not fast, it's not constant, it's still growing, but it's very, very slowly growing very slowly. So it's a very desirable runtime complexity. And you get it whenever you're, for example, dividing a list by 2. In divide and conquer algorithms, you always have at least some part of it is logarithmic, because you have a full list of, I don't know, 20 values, and what you do is you then say, okay, take half of it and discard the other half. So essentially you're halving the problem size. You have, instead of 20, you now have 10, and then you have it again and you have 5, and so on. And this is essentially in a way logarithm based too. So this is where this logarithmic runtime complexity comes from, and this is a very, very desirable one. If a problem is solvable in logarithmic time, and there are not a lot of problems that are solvable in logarithmic time, but if a problem is solvable in logarithmic time, it's a very, very easy to solve problem because it's very efficient. Now what you can also see here is the concept that we already talked about, that constants do not matter. So in this case, I choose 5 as a constant, and 5 is more than just, 1 times something. But logarithm is growing, and because of that, eventually it's going to always intersect with this constant line. Logarithm 10 is growing very slowly, so if I pick a huge number for the constant function here, so if I pick 5,000 or something, we're probably not going to be able to visualize it, because I would have to go to extremely high numbers, to 10 to the power of 5,000 in fact, to show you that this function intersects with the constant function. But it will intersect eventually, no matter how high the value is. But we can go to 10, for example, and you can see, yes, the logarithm is growing very slowly, but eventually in a very high numbers it's going to intersect. And I hope I'm able to visualize this here, not going out of range. Eventually it's going to pass the function and to dominate it. So you can say it's definitely limited by the logarithm. So the logarithmic function, obviously, since it's growing, is less efficient than a constant time. Now the next thing that you want to hope for, if you're not having a logarithmic function, if you don't have logarithmic growth and you don't have constant growth, what you want to have is linear growth. And linear growth is essentially just, okay, now the scale is a little bit too fucked up here. Linear growth is essentially the same amount of additional steps for each new element added to the problem. So for example, if I'm working with lists, one new element means X amount of steps. 2 new elements mean 2X amount of steps. X can be whatever. So in this case, I just have the function, let me just get rid of the constant function here. In this case, I have the function y equals X, which is essentially just a normal linear function. But any function that looks like that, like a straight line, is essentially a linear function. So I can go ahead and multiply this by 3, for example. It's going to be steeper. I can also go ahead and multiply this by a smaller number. So for example, I can go ahead and choose 0.2, for example, and it's going to be a more flat line here, less steeper line. But you can see it's still growing, and it's growing at a constant rate. So it's not slowing down the growth the way that a logarithmic function does it. It's actually having the same growth all the time. So of course, if I go ahead and pick a constant function here and give it a value like 9,000, it might be a large value, but eventually, sooner or later, if we scale that down, where are we here? 9,000, sooner or later, even with that 0.2x function, it's going to reach that state. As you can see, it crosses this function. So obviously, linear time is definitely worse than constant time. So whenever a function dominates another one, it's worse, because we're hoping for small values, not for large values. So we want to have slowly growing functions. So this is linear time, essentially the same amount of steps needed. So in some algorithms, when you add one more thing, you need to do one more step or 2 more steps. Whatever it is, a constant amount of steps for every problem. Whereas in other algorithms, you're going to have to add for each new thing. For example, if you're going to, let me give you a linear example. We already talked about it, is when you are looking for the maximum value of a list. When you're looking for the maximum value of a list, you need to go through all the elements in the list, and then you just pick the largest one. When you have one additional element, you just need to do one additional step. The same thing is if you have a list of numbers and you want to do 3 steps on all these numbers. So you go ahead and take each number, square it, divide it by 2, and then, I don't know, add 50 to it for whatever reason. These are 3 steps. And if you add one new number, you have 3 more steps. It's still linear because you have the same amount of steps. It's not depending on how many values are already in there. You have one n and that's it. Now, the next thing that we're going to look at is a combination of these two, of logarithmic time and linear time. And this is the so-called pseudo-linear time, oftentimes referred to as pseudo-linear time, because as you can see, it almost looks like a straight line because it's composed of the linear time and the logarithmic time. Its formula is n log n, which essentially means linear times logarithmic, and linear has a constant growth. It's just a straight line, and logarithm is essentially, when you look at it, it's growing, yes, but it's growing very slowly. It's almost not growing. It's flattening out. Over time, it's even growing slower. So the higher you get with pseudo-linear time, the more it actually looks like linear. So the more you progress, the more it looks like a straight line, even though it is not. It's a curve because you have log n as a factor, and log n is depending on n, so it's growing with the input size. So this happens oftentimes when you're working with divide and conquer algorithms. When we're working with merge sort, for example, quicksort, whenever we're splitting lists, whenever we're splitting problems and dividing them and conquering them, we're encountering this n log n time. For example, merge sort is an algorithm, sorting algorithm that we're going to talk about, that has a runtime complexity of n log n. Worst case, best case, I think, as well. And that's essentially it. You can now compare this to linear. Let's just choose a different factor here. Let's say this is 4n. So the linear function, you can see, okay, it's steeper, and you could say, okay, if that is linear, it should never pass the green one. But we can go ahead, scale down the coordinate system. You'll see it's not linear, it's just pseudo-linear, because eventually when we get to the bigger numbers here, I will definitely find a moment where this purple line crosses or intersects with the green line. And from this point on, as you can see, the purple line is now dominating the green line, which means that it's less efficient. However, practically speaking, it's almost the same. It's definitely growing faster than a linear time, obviously, but it's still a very good runtime complexity. So if you can solve a problem in n log n time, it's still very efficient. Next up is the so-called quadratic time. And now we get into some runtime complexity that is not as efficient anymore, because now we have pretty fast growth. Compare this to something like for x, rapidly outpacing it, rapidly getting more inefficient, less efficient than it. Also n log n, even if I add something like, I don't know, 50 to it, 50 times n log n, the turquoise function here is going to outpace this function very quickly because it grows very quickly. Even if I pick 50, it doesn't matter because n squared is growing way faster. So we don't even have to go to extremely high numbers here. You can see it happens at 100 already. It's outperforming, or not outperforming, actually outgrowing it, which is bad, so not outperforming. And n squared is essentially a runtime complexity that you're going to encounter very often. It's whenever you have to consider all the other elements that are already in the list and perform each operation on each element. So I hope this is not too confusing, but we talked about this already. If I have a list of numbers and the job of the algorithm is to take each number and multiply it by itself and all the other elements, then go to the next element and do the same thing with all the other elements and itself. When I add a new element, it's not just that I have to do this for the element, I have to multiply this element with all the other elements and itself, which has a dependence to the amount of elements already in that list, but I also have to go back to the other elements and multiply the other elements by this new element, so I have something like n squared. So compared to something like linear time, pseudo-linear time, logarithmic time, it's not desirable, not efficient. A lot of sorting algorithms that are less efficient are considered to have a runtime complexity of n squared. For example, bubble sort has a worst case runtime complexity of n squared. I'm not sure if it has an average runtime complexity of n squared. I think it has. But n squared is essentially not good. But for some problem again, for some problems again, it is, because if you can solve a problem like sorting in n log n, of course, n squared is very, very unattractive. But there are a lot of problems out there, and if we were able to solve them, some of them in n squared time, in big O of n squared, so to say, that would be a revolution. So n squared, even though it's very slow and inefficient compared to log n or to linear time or pseudo-linear time, whatever it is, it's still very, very efficient compared to exponential time, because n squared might not be as efficient, but it's solvable. It is doable. We can work with n squared. It may take longer, it may take long, but it's not necessarily something that's impossible to solve. We can definitely work with n squared. Same goes for anything that is n to the power of a constant, so n to the power 3, n to the power 4, n to the power 5. Yes, n to the power of 3 is growing faster than n to the power of 2, but still as long as it's of the format n to the power of some constant, it is still polynomial time and it's solvable. We can work with it, and we consider these, I don't know if possible is the right word, but manageable problems. We can work with them. And now we're getting to the functions, to the runtime complexities that we consider not manageable. These are runtime complexities that you really want to avoid. You don't want to have them. And the first one is exponential growth. Exponential growth means you have a constant to the power of n. So up until now we had n to the power of a constant. Now we have a constant to the power of n. And this constant can be 2, this constant can be 4, whatever it is. It essentially means that n is the exponent. So compare this with x to the power 3. This red function here is 2 to the power of n. And this yellow function is n to the power of 3. Even though it might seem as if this function is growing faster, 2 to the power of n is definitely going to pass this. So let's just scale this down a little bit, and you can see it's passing it quite quickly already at x equals or n equals 10. You can see that the red function is already outgrowing it by a substantial amount and very fast. Exponential growth is really dangerous. This is what you really want to avoid in any way. It's extremely fast growth, and even if you don't pick 2, as long as the number is larger than 1, obviously, because 1 to the power of I don't know, 1 million is still 1, but as long as you have something like 1.1 to the power of x, it is still going to outperform these other polynomial function, even if it takes a little bit longer, but we don't even have to wait too long. It's exponential growth, so the growth itself is growing really fast. And as you can see in like 150, even though I'm dealing with 1.1 to the power of x and x to the power of 3, you can see it's outperforming it easily. And you can do the same thing with, I can also say, I don't know, 50 times x to the power of 3, and I still have 1.1 to the power of x. It doesn't matter. Again, outperformed. And we're at very small numbers here. So I can go ahead and do this with 500. I can play around with this. You're going to see exponential growth. You don't want to fuck with it. It is really not something you want to work with. Exponential growth is outperforming everything. I can also go ahead and say x to the power of 5. Who cares? It's going to take longer, but sooner or later, okay, I cannot, oh yeah, I can. I can even scale it down at around 360, 370. 1.1 to the power of x is dominating 500x to the power of 5. So you can see polynomial time is nothing compared to exponential time. This is really something you want to avoid. And how does this come into existence? For example, if you have recursion sometimes. For example, if you want to implement the Fibonacci sequence recursively, what you can do is you can go ahead and write a recursive algorithm of start with 2 fixed values, like the first one is 0, the second one is 1, and then what you do is you do 2 recursive calls, and you essentially say, okay, give me the last number n minus 1 and the second last number, which is n minus 2, and essentially what you're doing is you're having recursive calls, and for each 2 recursive calls, and for each of those you have 2 recursive calls again, and for each of those 2 recursive calls again, if you don't using dynamic programming or anything like memorization or something, you're running into exponential time. And this here is 1.1 to the power of x. If I increase this to like 5, you have no chance. Like, this is extremely fast growth. And exponential growth is definitely something you want to avoid. Just keep that in mind. But it gets even worse, because exponential growth is not the worst thing that you can have. You can also have factorial growth. And factorial growth, for those of you who don't know what factorial is essentially, if you have n factorial, this means n times n minus 1 times n minus 2 and so on until you get to 1. For example, if n is 50, it's 50 times 49 times 48 times 47 until you get down to 1. And this is I'm not going to say outperforming again, it's dominating, it's limiting it's essentially worse than exponential growth. So as you can see, even if I pick something like, I don't know, let's go with 9 to the power of x, even though that's a very fast growing exponential function, we're going to see that this factorial function here is definitely going to intersect with that red function. I hope we have enough scale here to show that, but I think it should be possible. Otherwise we have to lower the exponential constant a little bit. We have to lower it. Let's go with not 9 to the power of x, but 7 to the power of x. 7 to the power of x. And now you can see it happened somewhere down here. The green function passed the red function because factorial growth is faster than exponential growth, because essentially you're multiplying n times n minus 1, which gets you gets you into very high numbers quite quickly. So this is even worse, but fortunately it's not happening too often. It happens when you try to find out all the possible permutations of elements, for example, but factorial time is not something that usually will happen to you in a normal algorithm. But even if you think factorial is the worst thing, there's one thing that's even worse, but it's just something I want to show to you. It's not really something that happens quite often, and it's n to the power of n. So it's exponential growth, but not only the exponent is growing, but even the constant, so to say, the variable, the base is growing. So this is the pink function here, x to the power of x, and this is an extremely rapid growth. So you can see it's going to dominate these functions quite quickly and forever. So this is even worse. So if you have x to the, or n to the power of n, it's worse than factorial, but I cannot really think of an example where this is going to happen. So this is just to show you that it's even worse than n factorial. But the worst thing that you can realistically encounter in a normal algorithm is going to be n factorial, or most of the time it's going to be exponential. And exponential is something that we cannot really manage. So if something is only solvable in exponential time, it's very, very hard for us. And if we don't have any polynomial solutions, we cannot really say that we have a good solution to the problem. Now, before we get into the actual analysis of this algorithm that you can see here on the screen, I want to mention that this episode is going to be very mathematical. So it may be the case that your high school level math knowledge that I talked about in the first video may not be enough. However, the topics that are covered in this video are not essential, not mandatory, so you don't need to know all the mathematical operations that we're going to apply here. So in a sense, if you're not interested in the exact mathematical analysis of an algorithm, you can skip this episode or just watch it without understanding every single thing, and you can proceed watching the next videos. However, if you're interested in mathematics and you're at least familiar with the so-called sigma sum notation, which is this thing here, like sigma sum from I equals 0 to n of something. If you're familiar with this thing, this episode should be not necessarily easy, but understandable to you. So this is what we're going to need in this video, definitely. Now, let us look at this algorithm here. The algorithm here, we're not going to talk too much about its functionality because everything it's doing, or all it's doing, is essentially just adding numbers to k and then returning k. So in a sense, we're just adding, and then ending up with a value k that we return. But the question that we're asking here is, how many primitive operations do we have? So let's go ahead and naively just analyze the algorithm. We can say, okay, this k equals 0 is just one primitive operation. And then we have a loop, and the loop in and of itself is not necessarily a primitive operation. We could say it is, whatever. But the question here is, inside of this loop down here, or inside of this loop, first of all, we have another loop, but then we have a statement, which is also just one primitive operation, and the return is also one primitive operation. So to determine the amount of primitive operations, we need to figure out how many times this statement gets executed, because this statement is one primitive operation, okay? And this statement is also one primitive operation. We don't really care about these two because they're basically just a constant plus 2. So we can actually ignore them when it comes to the runtime complexity because they're not important. As you can see, this is one statement, another statement, then we have loops in between. So this statement here is interesting because the k plus j plus I statement gets executed as many times as these two loops are being executed, or as many times as these two loops iterate. So the first one is easy because we're starting I equals 1 and then we're going up to n. So we essentially have 1, 2, 3, blah, 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 up until n. So in a sense, this is just n times. We execute this loop n times. However, this statement gets executed more than n times because we don't execute it n times. We execute the loop that executes the statement n times. So this thing here gets executed n times, and how many times it gets executed itself. So how can we figure out how many times this loop gets executed? In a sense, we have just I plus 1 to n, but the I, and this is a tricky thing here, the I is constantly changing. We don't have a number like 4 and then we go up until n, but we have a constantly changing number. So the first time we go from 1 plus 1 is 2, 2 to n, then we have 3 to n, then we have 4 to n, and so on, until we get to I plus, or actually n plus 1 to n, which is actually over the limit, so we don't care about it. But how we can go about this is to write down the pattern. So what do we have? The first time we go from 2 to n, as we already said. So we have 2 to n. This is how many times this loop gets executed. One time, 2 to n times. What is this? This is essentially just n minus 1 times. Because this here, 1 to n is n times, we have n minus 1 times. Then we have 3 to n. 3 to n means it gets executed n minus 2 times, and so on. So in a sense, we keep going like that until we get to n minus n times, because that is essentially just 0 times, which in a sense means that we're just executing this n minus 1 times plus n minus 2 times plus n minus 3 times, and so on, until we get to 3, 2, 1. This is the thing that we need to calculate. This also is already including this loop here, because in order to have this scaling up, have this I increasing so that we get to n minus 1, n minus 2, n minus 3, and so on, is because this loop here is iterating. So we have two loops, and in total, this statement gets executed that many times. I hope everything is on the screen here. But this is essentially what it is, right? So what we can do here to figure out what this actually means, because this right here is just, a pattern. We cannot really say what the runtime complexity is based off of this thing. So what we need to do is we need to write it down in the sigma sum notation. And the sigma sum notation is essentially just saying, okay, we write the sigma symbol here, and then we say, okay, where are we starting? And we're starting at I equals 1, because obviously we're starting at I equals 1, as is stated in the loop here, and we go up until n. And what do? We always say n minus I. This sigma sum notation essentially means, if we write something down like that, it's exactly the same thing as here. So we say it's n minus I, and in the first iteration I is 1, so it's n minus 1, and then it's plus, so because it's the sum of all the individual parts. Then we say, okay, n minus I, and this time I increases by 1 because it's going towards n. So we have n minus 2, and so on. So this is the sum. And the beautiful thing about this sum here is that it can be rewritten in a different way. And this is the part where higher level maths come into play here. But we're not going to talk about these too much because the tutorial series here is on algorithms and data structures, not on mathematics. So what we're going to do is we're just going to take this term here and put it into Wolfram Alpha. And you can see then what this means. So essentially we're just saying sum of n minus I equals 1 to n. This is how you write this down in Wolfram Alpha. And then this machine here, this computational intelligence, is going to return this statement to you. It's essentially just n minus 1 times n divided by 2. As you can see, n minus 1 times n divided by 2. So this is essentially it, and this is the runtime complexity. This is actually the actual amount of steps, the actual amount of primitive operations that we do, at least in this part here. So in this in these two for loops here. This is the amount of primitive operations that we do. Okay, we can add +2 at the end to get the total amount, but that is the exact number of primitive operations if we assume that this is one primitive operation and these loops are just running without any conditions that are also primitive operations or whatever. But even if there were, we can just go ahead and multiply by 3 or something, for example. Whatever, this is the exact amount. So in a sense, if we multiply this out, we get n squared minus n divided by 2. Divided by 2 is essentially just the constant factor 1/2, so we can just ignore it, and we have n squared minus n, and this leaves us with a runtime complexity that is in theta, so exactly n squared. So this algorithm here, we just analyzed it, has a quadratic runtime complexity. So an additional thing that we can do here, just in order to do some mathematical exercise here, is to come up with a formula for the return value and specify it in a theta notation. Now you might say that's not very useful, but it's actually something that I had to do in my college exam and exercises. So we're going to do it here as well, because it gives you an additional opportunity to practice your sigma, sum, and logical thinking skills. So what you do here is you analyze how does this return value k come into existence. Now in every iteration, or with each iteration here, we add j and I. And instead of looking at j and I combined, we're going to look at them separately. So to come up with k starts at 0. And then we always add a j and an I to it. We're going to start by analyzing the I value, because the I value is actually more simple. We already figured out that this second loop here runs n-1 times in total, then n-2 times in total, and so on. And with each n-1, n-2, with each n-I, the I is obviously changing. So what we do here is we say essentially, when we have I equals 1, this loop runs n-1 times. So we have 1 times n-1 times. Then when I is 2, this loop runs 2 times, or actually not 2 times, but it runs n-2 times, with I being the value. So in the first iteration here, in the first iteration of this loop here, in the first loop, the second loop runs n-1 times, and each of those times we add 1 as the I value to k. So we have n-1 times 1 added to k in the first iteration of this first loop here, of the outer loop. Then I gets increased by 1, it is 2, and we get into the second loop again n-2 times, and I has the value 2, so we add 2 n-2 times to k. And this continues on and on. So essentially we have, every time I has a certain value, it gets added to k n-I times. And this is exactly what we're going to write down in the sigma notation. So we can say sigma of I equals 1 up until n. We're essentially just saying it's I times n minus I. This is the amount of, or this is the part of the sum that we add to k when we just look at the I. So we have the j component here, and we have the I component here. And how many times do we add I? Or not actually how many times, but okay, let me rephrase it in a different way so that I don't confuse you too much. This thing here that we're calculating in the end, so whatever we get out here, is what happens by adding this I in this loop constellation here. So we're adding j and I, and if we ignore the j and we just look at the i's added over time, this is what we get, this notation here. And we can again go ahead and put this into Wolfram alpha. So this time it's not just n minus I, but it's I times n minus I. So like that. And this gives us the following formula. So n-1 times n plus 1, and this divided by 6. So n minus, or it's also fine like that, n times n-1 times n plus 1 divided by 6. Which is, again, we can just multiply this out, n squared minus n times n plus 1 divided by 6, and this is just n to the power of 3 plus n squared minus n squared minus n. So this cancels out, divided by 6, and we end up with n to the power 3 minus n divided by 6. This is the actual number, the actual value that we get by adding these i's here. So we've covered that already. We're now going to look at the j part. Now the j part is a little bit more complicated because the amount of times we add j is the exact same that we add I, but j is constantly changing. And not only is it changing in the same way that I is changing, because I is changing only when this loop is iterating, j is changing in every single calculation. But we can look at it very simply. When I is 1, when I is 1, we start with 2, or we start at 2. So what happens is we add j, we have essentially the 2, we add j here one time as the value 2. So j has the value 2. It starts at 2, goes to n, and it gets added as 2. Then it gets added 3, 4, 5, and so on up until n. Then once this is done, once it's executed n minus 1 times, what happens is we increase I by 1, and we start counting at 3. So we have 3, 4, 5, and so on up until n. Then again, I gets increased by 1. We start counting at 4, or from 4, which means that we start here, 4 plus 5, and so on up until n. And as you can see, you can spot a pattern here. The value 2, j equals 2, happens only a single time. And this is the case when I equals 1. In the very first iteration of the second loop, when I equals 1, we add the number 2 to k. J equals 2 to k. This never happens again. Then we do the same thing for 3, 4, and so on, and then we increase I by 1. Then we add 3 one more time. So in total, 3 got added 2 times. 4 got added 3 times. If we continue like that, you'll see 5 gets added 4 times, and this is the exact pattern. So the j value, in a sense, if you spot the pattern and analyze it, you'll come up with the solution that the j value gets always added j minus 1 times. So if we have 2, 2 gets added 2 minus 1 times, which is 1 time. 3 gets added 3 minus 1 times, which is 2 times. So j is actually nothing but j minus 1, which looks similar like this one, but we don't have n minus j, but we have j minus 1. And this is the actual result for the j component of the sum. So j equals, now the question is, do we start at 1 or 2? I think we start at 2. Yes, of course we start at 2. Or actually, we could also start at 1, doesn't matter, because you would end up with 1 minus 1, which is 0, so it's actually the same sum. So j equals 2 up until n, and the expression here is j times j minus 1. And this again is something that we put into Wolfram Alpha, and j, actually we can do it with I as well, doesn't matter. We just have to remember for our own formula that it's j, so I minus 1, I equals 2 to n. And the result of this thing is the same, just divided by 3, so not by 6. So we have again n minus 1, n plus 1, divided by 3 this time. So we'll end up with the same expression here, which is n to the power of 3 minus n divided by 3, which again means that k is nothing but n to the power of 3 minus n divided by 6 plus n to the power of 3 minus n divided by 3. Now we could go ahead and multiply this by 2, so we would have n minus n to the power of 3 minus n plus 2n to the power of 3 minus 2n divided by 6, and this in total would give us 3n to the power of 3, or 3n cubed, minus 3n, and I think we would be able to then just extract 3 and cancel it out, so we would end up with n to the power of 3 minus 3n divided by 2. This is the formula for the k value, so you could say that the k value is in, if you want to specify it like that. We had to do it in university, that's why I'm doing it. I don't really understand why this is important to specify theta notation, but essentially this would be in theta of n cubed. So cubic runtime. Not really runtime, but cubic mathematical expression, whatever. So I hope this was not too confusing. Now, for those of you who are still here and haven't given up yet, we're going to cover the second algorithm. I'm proud of you that you're still here. We're going to talk about algorithm B here. And algorithm B is a little bit different. It's not that complicated to analyze, but it might be a little bit tricky because you have to think of things of high school mathematics that you've maybe forgotten already. So it's a good exercise. So let's go ahead right into it and start analyzing the runtime complexity. So k equals 0 is again one primitive operation. I equals 2 to the power of n is one primitive operation. In here we have one primitive operation, and in the end we also have one primitive operation. Now the only question that we have here is how many times does this while loop iterate or execute? And this is a little bit harder to see directly because we don't have a full loop that tells us from I to n, which is obviously n times, or from I equals 0 to n. This time we have a starting value 2 to the power of n, and we want to get this value down to 0, or actually down to 0 or below. So this is the condition for the loop. We start at 2 to the power of n and we want to get to 0 or below. And what happens to I is we always have it. This is this line here. In this line, you can see that I gets halved every time. So it's divided by 2, divided by 2, divided by 2, and of course floored. So this mathematical sign here, if you don't know it, means floor, which means that you round the number down. So if you have something like 2.5, the floor function gets it to 2. If you have something like 3.76, it gets it down to 3. If you have something like 7.98, it gets it down to 7. This is the floor function. And this is what we're doing here all the time. So the question is, how many times do we need to have 2 or divide by 2 to the power of n in order to get to 0 or less? And this is actually not that difficult to figure out if you understand what a logarithm is. And the logarithm essentially is exactly the question that we're looking at. So let's look at the logarithm base 2 of a number x. The logarithm base 2 of a number x actually gives you a result, and this result is the amount of times that you have to divide to multiply 2 by itself to get to x. So if the result is y, the number of 2's that we have here is y. So put in a little bit more simple words, when we calculate the logarithm of a value to a certain base, it tells us how many times we need to multiply this base by itself in order to get there. So if you have 2 to the power of n, this doesn't mean anything else but 2 times 2 times 2 times 2 times 2, blah, 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 n times. This is the definition of 2 to the power of n, obviously. So this is n times. So the question is, how many times can we divide by 2 in order to get to 0? And the answer obviously is n plus 1. Because when you divide 2 to the power of n times, you get to 1. And if you divide 1 by 2, you get to 0.5. And if you get to 0.5, you essentially end up with the floor function rounding it down to 0. And even though we don't need to use the logarithm, in a sense, there is the logarithm in here, because what we're doing is we're asking, what is the logarithm base 2 of 2 to the power of n? And obviously it's n. This is essentially what we need to do to calculate the runtime complexity of this particular algorithm, because we want to know how many times can I divide a certain number in order to get it down to first 1, and if you then divide 1 by 2, you get to 0, because this question is asking how many times do I need to do it in order to get to 1, but we can then add one more time to get to 0. So this is the result here, n plus 1, which means that we have a runtime complexity of theta of n, linear runtime complexity for this algorithm here. Now, coming up with the formula for the return value is also not that difficult in this particular case, because the only thing we're doing is we're adding I squared. And I starts at 2 to the power of n and gets decreased or divided by 2, halved essentially, with each iteration. So what we do is we have 2 to the power of n, then we have 2 to the power of n minus 1, then we have 2 to the power of n minus 2, and so on until we get to 2, 1, and 0, which is essentially irrelevant. And what we're doing is we're constantly adding these things squared. So we have 2 to the power of n squared plus 2 to the power of n minus 1 squared plus 2 to the power of n minus 2 squared, and so on, 2 squared, 1 squared, and then 0 squared, which is nothing. And then we add all these things, and this is actually the formula for the return value. So put into different words, we have sigma I equals, let me think about this, we have 2 to the power of n minus, then 0, n minus I squared. This is the formula. We have 2 to the power of n minus I is constantly changing and increasing until we get to n minus n, which is 0, which is 1. And then we get, we take the result and square it. And this is the exact thing that we need to look at. So we're going to type it into Wolfram Alpha again. We have 2 to the power of n minus I and the result squared. Let's do it like that. And we start at 0. And the result is 4 to the power of n plus 1 minus 1 divided by 3. 4 to the power of n plus 1, 4 n plus 1, was it minus 1? Yeah, divided by 3. This is the formula for the return value, the runtime complexity in a sense for the return value. It's not a runtime complexity, it's the complexity of the return value, you could say the size of the return value. And actually that's maybe the reason you specify the theta notation, to know how big it gets, to have a size complexity in a sense. And we can just ignore the divided by 3, we can ignore the 1. And 4 to the power of n plus 1 is essentially nothing but 4 times 4 to the power of n, which means this is a constant factor that we can ignore, which means that we have an exponential complexity here because we have theta of 4 to the power of n, and 4 to the power of n is exponential complexity, size complexity in this case of the return value. So in order to explain greedy algorithms, I'm going to use a very simple example. Let's say we have 3 types of coins. So we have 1 cent, we have 5 cents, and we have 10 cents. These are the types of coins that we can use, and we have an unlimited amount of those. So now the question is, if I'm given a certain amount of cents, for example, 47 cents, how can I find the optimal solution when the goal is to get to that amount, to give the person this amount of cents with the least amount of coins possible, with the smallest amount of coins possible? So of course, if someone says, I want 47 cents and I have an unlimited amount of all these coins, I can just go ahead and say, okay, I'll give you 1 cent 47 times, but then I end up with 47 coins, which is not an optimal result. And the question is, can we find an optimal solution? Now to this problem, the optimal solution would be 10 cents times 4, 5 cents times 1, and 1 cent times 2. So we end up with 7 coins and a total of 47 cents. This is a very simple solution, an optimal solution. And the question now is not just how can you solve this for a particular number. For example, 127 would be another number that we can choose. The question is, can you find an algorithm, and we don't need to write down the pseudocode, just by logical thinking, can you find an algorithm that always gives you the optimal solution? And it's not obvious that any algorithm that seems intuitive will work here. So now what we did in the first example here with 47 cents, for example, is we just looked at, okay, what is the largest coin here? 10 cents. Okay, how many times can I use 10 cents in order to get to 47? Okay, I can use it 4 times. So I end up with 7 cents left, and then I can use the 5 cents. Then I have 2 cents left, so I can just go ahead 1 cent times 2, okay? Now, what we're doing here is applying a so-called greedy algorithm. And a greedy algorithm is defined by always picking the solution, the local solution, that seems the most beneficial right now. So you're not looking long-term. You're thinking, okay, what decreases the value of the price here? So we have 47 cents. Decreasing 47 cents the most with one step is done by subtracting 10 cents, right? It doesn't have to be the case that subtracting 10 cents is necessarily the best solution long term. Maybe if I subtract 10 cents now, it's going to be a problem later on. Now I can spoil the surprise for you. In this case, in this constellation, the greedy algorithm will always give us the best result. So actually doing this and picking the largest possible number will give us the best results in this case. But this is what a greedy algorithm does. It looks at the value 51, for example, and asks, okay, how can I decrease this value the most with my next step? It doesn't ask the question of how can I decrease it in the long run with the least amount of coins possible. It looks, okay, which is the next value that I can choose to decrease this number the most? And the answer is the largest coin. And we do this as long as the largest coin still fits into the value. And then we choose the other coins. However, it is not always necessarily the case that a greedy algorithm gives you the best result possible. For example, let's pick a different set of coins. So we have 1 cent, 5 cents, and 10 cents again. But then we can also add 20 cents and 25 cents. Now notice I'm not picking any prime numbers or something. I'm not picking any super crazy numbers here. These are ordinary numbers. And the goal now is to find optimal solutions. Now, of course, if I have something like 30 cents, I can go ahead and say, okay, 25 cents plus 5 cents is 30 cents. So I have 2 coins as the optimal solution. So sometimes it still works, but not necessarily every time. For example, let's look at 40 cents. And 40 cents is an example where this would not work because the greedy algorithm asks, what is the coin that I can use to decrease this value the most right now? The greedy algorithm is interested in the best solution locally. We want to decrease the value to 0. Okay, the best solution to do that right now, as far as I can see, is subtracting 25 cents. So, okay, what we do is we end up with 15 cents. Then I go ahead, subtract 10 cents, end up with 5 cents. And then we go ahead and subtract the 5 cents. And we end up with 0 cents using 3 coins. However, this is not the optimal solution because the optimal solution is not a greedy solution. The optimal solution is just picking 20 cents 2 times. 2 coins, and we still end up with 40 cents. So this is, as you can see, a proof that greedy algorithms are not always, especially not in general, but also not for this example where sometimes in some constellation, a greedy algorithm always gives you the optimal result. If you only use these 3 coins here, a greedy algorithm will always give you the optimal result. However, sometimes in different constellations, it's not going to be the case. So you have to be careful, and I just want you to know what greedy algorithms are, that sometimes they work, sometimes they don't work, and now you should know about this, and we'll see a lot of greedy algorithms in the future. So let us get right into the bubble sort algorithm. We're going to look at a bubble sort algorithm, which is a very inefficient sorting algorithm. I can spoil that surprise for you. It's mostly taught because of educational purposes. So you want to teach people what sorting looks like, what sorting is, and you start with bubble sort, insertion sort, selection sort, and so on. Later on, we're going to use divide and conquer algorithms like quicksort and merge sort. We're going to talk about these as well. But let's start out with bubble sort. Let's say we have a list like 4, 6, 5, 2, 1, 3. This is the list that we have, and we need to sort this list. Now, the bubble sort algorithm has a certain way of solving this problem. We talked about problems already. Problems are goals that we have, tasks that we want to accomplish, and an algorithm solves these problems or this problem using a set of instructions. So this problem is sorting the list. We want to end up obviously with a list that looks like this 1, 2, 3, 4, 5, 6, and we want to do this in an algorithmic way using a set of instructions. Now the bubble sort algorithm, before we go into the actual pseudocode and the actual steps, we're going to just talk about the intuition here. basically what it does is it takes the first number here and compares it to its neighboring number, to the next number. And you can see 4, 6 is in the right position, so we just accept this as sorted. We accept these two numbers, each other, or in their context of these two numbers, they're sorted. So 4 is less than 6, and that's fine. When we have done that, we have looked at the first two positions. Then we look at the second position. We take 6 and compare it to its next neighbor, so to 5. And you can see 6 is less than 5, which is 6 is larger than 5, but it's in the position before 5, so that's not okay. And we swap these two numbers. So now we end up with 4, 5, 6, 2, 1, 3. Then what we do is we compare 6 to 2, and we see, okay, 6 is again larger than 2, but in the position it's before 2. So we say 4, 5, 2, 6, and so on. And you can see where this goes. It basically says, or it basically ends up with 6 in the end, and all the other elements get swapped before 6. So you get 4, 5, 2, 1, 3, 6 in the end. Now, as you can see, this list is not sorted. Why is it not sorted? Because we only positioned one element where it should be. Only the element 6 is in the right position in this case. So what we can do next is we can just repeat the process. So we go ahead and say, okay, 4, 5, still all right. 5, 2 is not all right, so we have 4, 2, 5. Then again, we compare it to 1. We can say, okay, it's also 4, 2, 1, 5. 3, the same shit. So like that. And the question now is, how many times do we need to do that in order to sort the list? And as you can see, in each iteration, we have one element that is at the right position. Basically, what we're doing is we're filtering out the largest element and shifting it as right as possible. So we started with 6. We noticed that 6 is the largest element. And then whatever we compared it to was less than 6, so it ended up in the maximum position, the last position. Then 6 was already the maximum, and we repeated the process. 5 was the largest number, so every time we met 5, we put it, we shifted it to the right. Now, of course, in this list, this may be the case like that, but sometimes you're also going to have something like 3, 2, 1, and then 5, or not 5, let's say 6, 5, 4. So you're going to shift values that are not the maximum values. So 3 and 2 is also not the right order. So you're going to say 2, 3, then 2, 1, 3. Even though 3 is not the maximum number, it's the maximum number of this subset here. So you're always going to just pick one number and then swap it if it's not in the right position compared to its next neighbor. So you're going to look at, is this number, is it justified that this number is before the other number? So 3 is larger than 2, but it comes before 2, so that's not justified. We swap it. Then the same thing with 3 and 1. But then you see, okay, 3 and 6, you can see 3 is less than 6, so it's justified, and 6 is the new number that we're going to look at. And then 6 is larger than 5, so it's not justified, and you swap it, basically. So since one element, with each iteration, one extra element at least is ending up in the right position, this has to be done a maximum amount of n times, because when you do this n times, this process that we just discussed, you're going to end up with a sorted list, because in the first iteration, 6 is at the right position, then 5, then 4, then 3, then 2, then 1, and then the list is sorted. At least, or at a maximum iterations of n, or after a maximum of n iterations, you're going to have a sorted list, because then you have put n elements into the right position, and the list has n elements. So this is the basic intuition behind the bubble sort, and we're now going to look at the pseudocode. So now let us look at the pseudocode here, and this pseudocode is a very simple one. Basically, the first line just tells us this is a function called bubble sort. We pass a list to it. This list can be whatever it is, 1, 2, 7, 6, 3, 4, whatever. You have a list, and you pass it into this function, and then you have two loops. The first loop runs from I equals 0 to the size of the list. So if you have 1, 2, 3, this is a list of size 3. If you have 5, 6, 6, 7, 8, it's a list of size 5, obviously. So depending on the list size, you can say the list size is n, and then you already can see that this loop runs n times. So n is a list size, and we run a loop from 0 to n to the list size. Inside of that loop, we run another loop from j equals 0 to the size of the list minus I minus 1. This might be a little bit confusing. Now, first of all, this first loop here tells us that we need to run this whole thing n times, because we're not checking is the list already sorted. So if you have the list, for example, 1, 2, 3, 4, 6, 5, after one iteration it's going to be sorted, but we don't check for that, so it's going to run through all these loops, through all these iterations, even though the list is sorted already. We don't check for that in this particular algorithm, in this particular pseudocode. So what we do is we definitely run this loop n times. The process that we just discussed of comparing, we run this n times. But we don't compare all the digits. So if you have a list like 5, 6, 4, 1, 3, 2, after one iteration, we set already that one element is going to be at the right position. So you're going to end up definitely, no matter what you do in between, the 6 is going to be at the last position. So we don't have to care about the 6 anymore. We don't have to care about the maximum element. It's going to be sorted for itself. It's in the proper position. Doesn't matter what happens to the list in between. If we swap 4 and 5, if we swap 1 and 4, it doesn't matter. The 6 is going to end up in the maximum position where it belongs. So we can ignore the 6 actually. No matter what the list looks like, the 6 is sorted already, and we can go ahead and say, okay, we only have 5, 4, 1, 3, and 2 to sort. So we sort one less element. After one iteration, we have one less element to look at. And this is why we subtract I here, because I is essentially how many iterations did we have already. Because what happens if I had 2 iterations? If I had 2 iterations, the 6 is at the proper position and the 5 is at the proper position as well, at least. There might be other elements that are also in the proper position already, but these 2 elements are for sure, without needing to check for it, these 2 elements are going to be at the proper position, at the position they belong to. So we can ignore the 5 and we have 2 less elements to look at. So with each iteration that we do, we have one less element to look at. So after 2 iterations, we have 2 less elements. After 3 iterations, 3 less elements. So I is the amount of iterations, and we subtract I, the amount of iterations, from how many elements we have to look at. And the minus 1 is very simple. If you have an array and you look, or a list, and you look at the element 6, you compare it to the next element. If you look at the element 4, you compare it to the next element. So you're not going to look at 2 because you don't have a next element. The only thing that you need to do is you need to look at 3 and compare it to 2. You don't compare 2 to something else. So you stop one element before you reach the list size. You don't look at the last index. This is what you basically do. And then what do you actually do inside of this loop is you compare the elements. So what you do is you say, I do this n times. And what do I do n times? I look at all these elements. So I compare 5 to 6. And if 5 is larger than 6, I swap the elements. In this case, it's not, so I ignore it. I don't do anything. Then I go back to the loop. Now I compare 6 to 4. Yes, 6 is larger than 4. I swap the elements. And I do this one iteration. Then I increase I by 1. And I only look at the first 5 of these numbers. So let's go through the process. We have 5. Then we compare 6 to 4. Then it's 4. Then 6 to 1, it's 1. 6 to 3, 6 to 2. And this is the list that we end up after the first iteration. So now I is 2, and we can ignore 6 because it's already sorted, and we only look at this list here. So I gets subtracted, 1 gets subtracted here. And I repeat the same process. So what I do is I compare 5 to 4. Okay, so we swap them, 4, 1, 3, 2, 5. And I can say, okay, 5 is sorted. Where's the red color? 5 is sorted, so I ignore it, and I only look at this list. And I do this n times, so in the end, I only end up with the 1 there, and the list is sorted. This is essentially what the pseudocode means. So let's use the mathematical skills that we already have in order to analyze this algorithm. And we can look at these 2 loops here, or actually before we do that, let's look at these 2 lines here. We have one primitive operation right here, which is a comparison, and one primitive operation right here, which is a swap. Since we're analyzing the worst case runtime complexity, what we need to do is we need to assume that every time we enter the if statement, so every time we have 2 primitive operations, this is the worst case. This would be a list like 6, 5, 4, 3, 2, 1. So every time we would have this element sorted, and it would end up in the end. But then we have this completely unsorted list and only 5 would change place. So every time we would have to go ahead and swap the elements. This is the worst case scenario for the bubble sort. This list obviously, or not list, sorry, this loop obviously gets executed n times because it gets executed as many times as the list has size, so as many elements that there are in the list. And the second loop here is being executed n minus I times. Now we can write this down in a sigma notation again, which essentially means we start at, and this is the tricky part here, we start at 1. I'm going to tell you why. And we have n minus I times, and this 2 times, because here we have 2 primitive operations. With each iteration, the amount of iterations is the outer loop times the inner loop. And why are we starting to count from 1? Because the first time we enter this loop, we compare the first element to the second element, the second element to the third element, the third element to the fourth element, but we don't compare the last element to anything. So we have n minus 1 operations inside there, or iterations inside there. So if we say n minus I and we start counting at 0, we would have an additional n that is just not accurate. We need to start from n minus 1 because this loop here, this thing here starts running from, actually this is not true what I wrote here, it's n minus I minus 1, but we're not going to write minus 1 in here, we're going to just increase the starting point of I by 1. This is actually the exact amount of steps that we need. I tried this with a Python script and it was the exact result, because you start counting from, when you start counting from 1, the first iteration of the second loop runs n minus 1 times, which is actually the case because it runs n minus 1 times. So this is why you start counting from 1. You have 2 times because you have 2 primitive operations. And again, we can just use Wolfram alpha to tell us what this is. It's the sum of n minus I from I equals 1 to n. This is what we're looking at. And you can see it's n minus 1 times n divided by 2. But remember, we have this 2 in front of here. So essentially what we end up with is 2 times n minus 1 divided by 2. So this cancels out and we can just ignore the 2 here. And what we end up with is, let me find the right color again, is n times n minus 1. This is, of course, n squared minus n. And this is, of course, in big O of n squared. We're going to specify the big O here instead of the theta notation because we're interested in the worst case runtime complexity, not in the average case or in the exact amount of steps. But there's a maximum of n squared steps that we need here. Like the runtime complexity is n squared. We talked about what that means already. So as always, we're going to start by looking at the intuition here, and the intuition is a very simple one. Selection sort is what we're going to talk about today. The selection sort feels almost like a reverse bubble sort. So remember in the last video we covered bubble sort, and we had a list that's say 4, 5, 1, 3, 6, 2, whatever. And in bubble sort, what we did is we compared the 2 neighboring elements every time. So we had 4 and 5 and we compared them, 5 and 1, we swapped them. And after one iteration, we always had the maximum element at its right position, at the maximum position. So 6 was done and we only had to look at the rest of the list. Now selection sort works similar, but in the opposite way. So what we do is we scan the list, we go through the list, and we scan this list for the smallest element, for the minimum element, in this case 1. And what we do then is we put it at the first position. So we swap it with the 4 in this case. And what we have then is 1, 5, 4, 3, 6, 2. And after one iteration, the first element is already at its right position and we can ignore it. And we have n minus 1 elements to sort. So this is the basic intuition here. So what we do is we essentially go ahead and say in the list in the beginning, what we do is we say, okay, I just assume this is my minimum element. So 4 is my minimum element. And 0 is my minimum index. So this is the position. We have 0, 1, 2, 3, 4, 5 is an index. And what we do then is we go through the list and we find the smallest element, or we find smaller elements in general. So in this case, it's a little bit unfortunate because we don't have any smaller elements before we get to the minimum. But let's say this was something like 2 here. then 2 would be considered the smallest element until we get to a smaller one. But now we go here through the list and we see, okay, 5 is larger, so we don't care about it. 1 is the new smallest element. We see, okay, 1 is smaller than 4. So what we do is we essentially say, okay, 1 is smaller than 4, so the new minimum is 1, and it is at position 3 right now, 2 right now. So we swap it, and then we have 1, 5, 4, 3, 6, 2. And then we continue on with the rest of the list, and we do the same thing until we have the list sorted. So essentially, it's like a reverse bubble sort. You always have one less element to care about after each iteration, but it's not the maximum, it's the minimum element. And the way you go about it is also not the same, because you don't compare two neighboring elements all the time, but you actually look for the smallest value and then swap it with the position of the former smallest value. So this is what we do in selection sort. So as always, let's look at the pseudocode to see what's going on exactly behind the scenes. And for this, we're going to create a list here. Let's say it's 5, 3, 2, 4, 1, 6. This is the list that we're going to deal with. And you can see we have the function selection sort here with the parameter list, which is the same structure that we had for bubble sort. And then the first thing that you see is the loop here that goes from 0 to size list, which is n. But we're going to talk about the runtime complexity in a second. We're just going to look at the code now and what it does. So then we have two variables here, min value and min index. So let's just go ahead and write these down. We have the variables min value, minimum value, and minimum index. So what we do here naively is we get into the list here and pick the first element. We pick the first element here, in this case 5, and just say naively it's the minimum value right now, okay? And the index it's at is 0. This is what we do. And then we have a second loop here for j equals I to size list, which is going from I to n. And in this case, it starts with 0 as well. So we just go ahead and say, okay, if the current element is less than the minimum value, we're going to consider it the new minimum value. So we go ahead and say, okay, 5 is not less than 5. It's the minimum value itself. So we just skip this and then we go through 3. Okay, 3 is less than the minimum value right now. So we can see, okay, list j, since j increased by 1, we're going to, we see that 3 is less than 2. So what do? We enter this if statement here, this if block, and see, okay, then the new minimum value is 3. We cross out 5 and we say 3 is the new minimum value. The index is 1. Okay, then we go ahead and say, okay, now we have 2. Compare 2 to 3. Okay, 2 is the new minimum value because it's less than 3. So we just go ahead and update these values. Then we go to 4 and we see, okay, 4 is larger than 2. So it's not the new minimum value. We just skip this one. Then we go to 1 and you see, okay, 1 is the new minimum value or is less than 2. So it's the new minimum value. And it's index 0, 1, 2, 3, 4. And then we also ignore 6 because it's larger than 1. So at the end of this loop, we have the last statement then, which is swap list I and list minimum index. The list I is the current index that we're looking at, which is 0. And then we also have the minimum index 4. So we swap 1 and 5 and we end up with a list that looks like this: 1, 3, 4, 1, 3, 2, 4, 5, 6. Then what we do is we increase I by 1. So in the same way that we did with the bubble sort with the last element in the bubble sort, we now ignore the first element in selection sort and we're only looking at this list here. So we ignore the 1 completely, and what we do is we say, okay, the new minimum value is I, so, or at index I. So what we do is we just say, okay, the new minimum value is obviously 3 and the index is 1. And then we repeat the same process. We go through the list, find the new minimum value, swap it, and we continue on and on until we get a sorted list. So let's go ahead and analyze the runtime complexity of this pseudocode here, of this algorithm, which is very easy actually in this case, because what do we have here? We have a loop that runs n times, then we have another loop that runs n minus 1 times, obviously, because we're going up until n, start at I, so it's n minus I times. And then we have primitive operations. We have 2 here. Okay, that's, so now 2 here, 2 primitive operations here. Then we have 3 primitive operations inside of this loop. In a worst case, of course, we're assuming that we're entering the if statement every time. This is the worst case of 3 primitive operations per iteration. And then we have swap list, which is one primitive operation. And this one primitive operation actually belongs to these two primitive operations because they're in the same loop. So what do we have exactly? If we look at it, we have a definite amount of 3n primitive operations. Why? Because this loop runs n times. So we have 3 primitive operations, 3 times n primitive operations, 3 primitive operations with each iteration, and we have n iterations, so we have 3 times n primitive operations. And then we also have 3 more primitive operations, but how many of them is the sum. Then we have, again, the sigma notation here, the sum of I equals 0 up until n, the sum of n minus I. So we can now go ahead and put this term again into Wolfram alpha. And we're going to see n minus I from I to 0, I equals 0 to n. We have n times n plus 1. And now we can go ahead and write it down like 3n plus 3 times n plus 1 halves. So in a sense, we just have 3n plus 3n squared plus 3n divided by 2. And we could just go ahead and multiply this by 2. So we would end up with 6n plus 3n squared plus 3n divided by 2, which is 9n plus 3n squared divided by 2. And this is just the exact amount. Essentially, we just have a runtime complexity of big O n squared because that's the largest exponent here. So it's a runtime complexity that is quadratic. And again, not a very efficient sorting algorithm. So let us start again with the intuition behind the insertion sort. As the name already suggests, we're going to insert numbers or elements where they belong instead of just swapping all the time. So what we're doing here when it comes to insertion sort is, let's say we have a list like 7, 7, 4, 8, 3, 2, 1, 5. Did I miss something? 6. There you go. This is the list that we have here. And now instead of going through it and swapping elements or comparing them, what we do is we split this list up imaginary in our head. We split it up into 2 parts, in the sorted part and the not sorted part. And in the beginning, the sorted part is just one number, the first element, this 7 here. And now what we do is we go through this list and we pick the next element and insert it into the sorted list. So we take this 4 here and then we insert it into the sorted section where it belongs. Now 4 is less than 7, so insert it before the 7. And the sorted part looks like this then. So we have 4, 7, and then we still have 8, 3, 2, 1, 5, 6, and so on. But that is now the sorted part of the list. So this is now the sorted part. Then we'll look at the next element, 8, and insert it into the list. In this case, it would be 4, 7, 8. So we write that down, 4, 7, 8. Then we have 3, 2, 1, 5, 6. And the sorted section is this here again. Now we get to 3. We're going to enter 3 here. Then we get to 2. 2 is here. Then we get to 1. 1 is here. Then we get to 5. 5 belongs here. And then we get to 6. 6 belongs here. So this is what we do. We take the list and we put a flag at a certain index where we say, okay, this is the barrier. This is on the left side, we have the sorted list. On the right side, we have the unsorted list. And then in the beginning, the sorted list is just one element because obviously one element is always going to be sorted. And then we pick the next element and insert it into the right position. The next element, insert it into the right position, and so on until we get a sorted list. So now let's go ahead and look at the pseudocode to see what's going on here. We have the insertion sort function definition here. We pass a list. Let's go ahead with the list 4, 6, 5, 3, 1, 2, something like that. And now what we're doing is we're having this list here, passing this list into the function, and we have the first loop here, which runs from 1 to n, to size of list. We're starting at 1 because we already said we have this boundary here, this magic boundary which says this is the sorted side, this is the unsorted side. So we're not going to look at the element 0, we're going to look at the element 1, 2, 3, 4, 5. So we're starting from index 1. And then we're saying, okay, the value that we're going to look at, the variable value, is essentially just the element at index I that we're currently at. So in this case, 6. And then we have a counter, so to say, which starts at the current index, which is 1, and it counts down. So what we do here is we say we have a second loop here, a while loop, not a for loop anymore. And we say while j is a positive number, because this is important because we decrease j here. We decrease it by 1 with each iteration. So as long as it's still larger than 0, and as long as the element at the index j minus 1 is larger than the value, we're going to shift the values so that new values fit in, so to say. So what we do in this case is we say, okay, j is still larger than 0 because it's 1, and list j minus 1, which is this here, 4 is not larger than the value. So what we do is we essentially just say 6 is already in the place where it should be, because if it wasn't, we would have to swap the positions essentially. But 6 is larger than 4, so we just leave it there, and the only thing that we do is we shift the boundary. Let me just find the yellow color again. There you go. This is the new boundary here. Now we go to the next thing. So we increase I by 1, and we now have 5 as the value here. So 5 is the value that we're currently looking at. Let's just pick the blue color again. 5 is the value that we're looking at. The index is 2. And now we say, okay, while j is larger than 0, it is, and list j minus 1 is larger than the value, and it is in this case because 6 is larger than 5. What do we do then? We look at the list j, which is 5 itself, and we say that this is just 6. So we swap this position. We just delete this here, and we say, okay, it's j minus 1. So we have two 6s right here, but we have the value 5 still saved in the variable value. So what we do next is we decrease j by 1. So j is only 1. And then what we do is we say, okay, j is still larger than 0. But in this case, j minus 1 is not larger than value. So 4 is not larger than 5. So we just leave it. And we say, okay, list j equals value. So at this position, we enter 5. This is how it essentially works. We just look for free, not for free spaces, but we start counting down from the actual position, and we look for larger numbers. As long as there are larger numbers, we're going one position back, and in the end, we just put the position, put the value that we're looking to insert into that position. And if we don't find any larger values at all, we're going to put it at index 0. So this is how it essentially works, and we're going to end up with the sorted list, which is 1, 2, 3, 4, 5, obviously. So this is what the pseudocode does. So let us now, as always, go ahead and analyze the runtime complexity of this pseudocode of this algorithm here. Let's start by pointing out the primitive operations. Here we have two primitive operations. Here we have one primitive operation. And here we have two more primitive operations. You can see that these primitive operations here, these two and this one here, are together because they're directly in the for loop. And this for loop, if you look at it, it runs from 1 to n. If it would run from 0 to n, it would be n times. So now it runs from 1 to n, which is n minus 1 times. So essentially what you can say is you have three operations that are definitely going to run n minus 1 times. So you say 3 times n minus 1. This is definitely true. And then you have this loop here, or this block here. And this block also runs n minus 1 times because of this loop. But how many times does this code run here? So how many times does this loop iterate? And since we're looking at the worst case complexity, we're going to look at the worst case scenario, which is, you start with j equals I, and you're decreasing j by 1 with each iteration if the condition is met. Now, in the worst case scenario, we're going to assume that it's always met. So what we do is we essentially just decrease j by 1 until we get to 0, because we just ignored this one here, since it's the worst case scenario. J is the same thing as I, so this thing runs I times. So what we can say is 3 times n minus 1 plus, and we have two primitive operations in here, plus 2 times, and we're starting I equals 0, or actually I equals 1, which is the same thing, because if you have, I'm going to tell you in a second why, up until n minus 1, because obviously we're running n minus 1 times. You can start from 0 or from 1 because it doesn't matter, because what we're going to sum up here is the I value. So if you have 0, it's just nothing. And you can ignore the 0 or add the 0, it doesn't matter. So this is what we're going to look at. 2 times the sum from I equals 1 to n minus 1 from I, or of I. And we can put this into Wolfram alpha again. We're going to say sum I equals 1 to n minus 1. This is what we're going to look at, and I'm going to show you. As you can see, it's 1/2 times n minus 1 times n, and if I change this to 0, it will be the same formula. As you can see, nothing changes. So this is the same thing as 3 times n minus 1 plus 2 times, so it cancels out because we have 2 times 1/2, and so we can ignore this. We can just forget about the 2 here, and we have n minus 1 times n. Now we're going to multiply all of this out. So we have 3n minus 3 plus n squared minus n. So we have 2n, or actually let's write it down like that. We have n squared plus 2n minus 3, which essentially means that we have a worst case runtime complexity that is in big O of n squared. So again, quadratic. As you can see, this is the runtime complexity of insertion sort. So let us start by talking about the divide and conquer approach, because we haven't covered it yet. And the divide and conquer term is a military term, and it comes from the idea that if you have an opponent that's too big, what you do is you divide them, you divide the people, you divide the armies into small sub-armies and conquer these armies individually. So the total result in the end is that you won the overall battle, even though you just conquered small armies. So if someone has 1,000 people, for example, you just split them up into groups of 100 people 10 times, and you conquer these 100 people 10 times, and in the end you won the overall battle because you conquered these 10 groups of 100 people, whereas you were not able to conquer the 1,000 people in one battle, right? And this is an approach that we also have in computer science, of course, not in a military setting, but in a programming setting. What you do when you have a complex problem is you divide it up into sub-problems. So you have one big problem here, one problem, and it's too big to be solved efficiently. You can solve it in quadratic time, cubic time, whatever. And what you do is you split it up into a couple of sub-problems here. Sub-problem 1, sub-problem 2, sub-problem 3, and so on. And what you do in the end is you conquer all these, you solve all these problems. Or maybe what you do is you split them even up into more sub-problems, right? And then once you have solved all these small sub-problems, these sub-problems are so simple that they can be solved easily. Then you combine all these sub-solutions into a solution to the whole problem. This is the idea of divide and conquer, and this is why we can sort in n log n time, in so-called pseudo-linear time, because we make use of this divide and conquer approach, which is also what we do with merge sort. Because when we have a list, 4, 8, 7, 1, 5, 6, 2, 3, or whatever, this is the list. What we do is we don't sort in a linear way. We don't sort the way in the same way that we do with bubble sort or insertion sort. We don't just pick a number and compare it to all the other numbers, but we take this list and split it up, for example, into 2 lists, then split this up into 2 lists, and so on, until we have a problem size that is so small that we can sort it efficiently or easily, and then we get these sorted sublists and combine them together. This is what we do in merge sort, and we're going to talk about this in more detail right now. So now let's look at what merge sort actually does. We're going to write down merge sort is what we're going to look at, the divide and conquer algorithm merge sort. What we do here is we have a list of numbers, again, something like 7, 3, 6, 8, 4, 1, 2, 5. This is everything, yes. So we have this list, and this list needs to be sorted. So what we do now is, or what merge sort does now is, it splits the list into 2 parts. So into the left part and the right part. Then we have 7, 3, 6, 8, and 4, 1, 2, 5 as separate lists. So what we do is we write them down, 7, 3, 6, 8, 4, 1, 2, 5, and then we recursively call merge sort onto these lists. So now we don't care about this right part. We call the whole merge sort algorithm onto this list here. And what this means is, of course, that we split it again. So what we do is we split it here in the middle again. Same goes for this list. And then we split this up into 7, 3. So 7, 3 is one list, 6, 8 is another list, 4, 1 is another list, and 2, 5 is another list. Then again, we call merge sort onto these lists and we split them up into 2 halves. And we end up with 7, 3, 6, 8, 4, 1, 2, and 5. So this is what we do. We have this tree here, this divide and conquer tree, where we split these lists up into 2 parts with each iteration. Or actually not iteration, but recursion. So what we now do is we have 8 lists with 1 element inside of the list. And what we do now is we have, this is the divide process. This is what we call divide. We get the list and divide it into sublists. And now we can start with conquering. So what we do now is we'll look at these 2 lists here. These are 2 separate lists and now we conquer them. So we sort them. And obviously 7 and 3, it's easy to sort this list. So what we do is we just combine them into a sorted list by saying, okay, it's 3 and it's 7. This is the one list. So we end up with the list 3, 7. This is the sorted list. We do the same thing for 6, 8. So it's 6 and 8. We do the same thing with 4, 1, 1, 4. 2, 5, 2, 5. This is how you merge them. This is the process of merging. You have 2 lists and you merge them. Now it's very simple when you have just 2 elements, 1 and 1. So you just have to compare those and you're done. But it's also not very complicated when you have more elements, because what you need to do now is you need to think about it. All these lists that you have here are already sorted. This list is sorted, this list is sorted, this list is sorted, all these lists are sorted, okay? So you don't have to worry about this number being larger than this number. You know that the lists are sorted. So whatever you want to do now, you know that these lists are sorted. So if you want to combine, if you want to merge these 2 lists here, 3, 7 and 6, 8, what you do is, in order to figure out what's the first element, you just have to look at the first 2 elements. So at this one, and at this one. You don't have to consider 7 and 8 because you know 7 and 8 are not the smallest value. So what you do is you pick the 3 in this case. So let me choose the yellow color again. Yeah, the 3 in this case. And then what you do is you only compare 7 to 6 because you know 8 is not going to be the smallest value again because 6 is definitely smaller than 8. Even though you don't look at 8, you know it because the list is sorted. So what you do then is, okay, 6 is the next one. Then you compare 7 to 8. It's 7, 8. And then you do the same thing here. 1 or 2, it's 1. 4 or 2, it's 2. 4 or 5, it's 4, and then 5. And then you do the last merge here by comparing these 2 lists. So again, you just look at 3 and 1. You don't have to consider all the other numbers. You pick 1 as the first value because it's smaller. Then you just look at 3 or 2. You pick 2. Then 3 or 4, you pick 3. Then 6 or 4, you pick 4. Then 6 or 5, you pick 5. Then 6, 7, 8 is already sorted. This is how you merge the list. And as you can see, this is a way more efficient way because you don't have to compare all the elements. You just compare the first 2 elements of the list or the first 2 elements that are left in the list in order to figure out how to sort the list. This is the process of dividing up until here. And then conquering or merging. So you can say you're dividing the list, the problem size here, and then you're merging or conquering down here. Conquering. This is what merge sort basically does. So let's go ahead and now analyze the runtime complexity of the merge sort. For this, we're not going to look at pseudocode because it would be unnecessarily complex to do that. We've done enough calculations. If you're interested in doing that, you can just type merge sort pseudocode. You're going to find a lot of resources on that. It wouldn't be very beneficial to you to just go ahead and analyze the merge sort again. We can do this with intuition as well because the merge sort, it's easy to understand. You can look at the code, you will understand it probably. But it's not necessary to analyze it by looking at each line of code because we can just intuit ourselves, intuit our ways into the runtime complexity of merge sort. It's not that difficult because what do we do here actually? We have 3 steps. First of all is we have the dividing. This is one thing. This is one part of the process. We divide the total list. Then we have the recursive call. Recursive call. And then we have the merging, right? The conquering, the merging, whatever it is, right? And what we need to do is we need to figure out what the runtime complexity of these 3 things is, right? And the first thing that we do is we divide. We have the full problem size n, we have n elements here, and then we have n half elements per side here. Then we have n divided by 4 elements and n divided by 8 elements over time. And essentially we do this until we get to single elements. So if you have 16, you're going to divide one more time. If you have 32, you're going to divide 2 more times, and so on. You're always going to divide the list until you get to single elements, to separate elements. And this is also true if the number of elements is not a power of 2. So if you have like 7 elements here, it's also you can also go ahead and split into 2. The point is, if you have a list like 3, 2, 5 and you divide it, you're going to say, for example, here is the middle, or here you can decide. And then you have 3, 2, 5, and then you have again one more time 3, 2. Oh, sorry. You have 3, 2, and 5 separately, right? So how many times do we need to divide the list in order to get to single elements? It's essentially just the logarithm of base 2 of n. Because you have n elements, and how many times you need to divide n by 2 in order to get to 1 is the exact definition of logarithm. So formulated the other way around, it would be how many times do I need to multiply 2 by itself in order to get to n. This is what logarithm base 2 basically means. And this is the answer here, right? So we have 8 elements, and 2 to the power of 3 is 8. So we have 3 levels, or 3 times division. 1 time, 2 times, 3 times, right? So this is how you divide it. You have a logarithmic runtime complexity when you divide the list, when you split it up. Of course, if you have 16 elements, it's going to be 2 to the power of 4 and so on. And again, also if you have 7 elements, it's also going to be 2 to the power of 3, because 8 is the next power of 2 that comes after 7, right? So we're not only interested in the exact value, but also in the next, we're actually interested in the next power of 2 in this case. So this is the first thing. This can be done in logarithmic time, right? And then we have the recursive call that essentially calls the merging process. So we're done with the splitting, where we have the individual elements here, and now we want to merge them. And let's first talk about step 3 here, the merging. How many operations, or what runtime complexity do we have when it comes to merging? Let's look at the last level here, that we have 3, 6, 7, 8, and 1, 2, 4, 5. Now in the worst case, we need to merge, or we need to have a linear amount of comparisons. Why? Because I need to compare the first element of this list with the first element of this list. And I need to do this until I have all the elements down here. So in the worst case, I have linear runtime complexity. And this is true for every merge. So we can say that this can be done in linear time, at least in the last level, but this is also the case for the formal levels. Because if we have 3, 7, and 6, 8 here, the runtime complexity is still linear, but the problem size is a different one. So in this case, we have 4 elements instead of 8 to merge. Sorry, I'm always clicking this button here. We have 4 elements instead of 8 to work with, but at the same time, we have this 2 times. So we don't have 8 elements, we have 4, but we have 2 times 4. So we have 8 in total, which is still linear for this level. And then we have here 2 elements, but we have this 4 times. So we have 2 elements here, 2 here, 2 here, and 2 here. So we always have n merging operations, or a linear runtime complexity per level. So we have linear time here. And if this was everything that we need to consider, it would be linear runtime complexity. But the point is, we do recursive calls, and we do the linear operation as many times as we need to get back to the full list size. So the dividing is logarithmic, but what we divide, we need to merge again. The merging is linear, but we need to merge as many times as we divided in order to get to the full list size again. So we have a logarithmic split, then we merge them, and we need to do this merging as many times as there are levels. As many times as we divided the list, we need to combine it again. So in total, we need to do this linear process logarithm of base 2 of n times. So the full runtime complexity in the big O notation is the logarithm of n times n, which is pseudo-linear. Because the process of merging is linear, but we need to do it as many times as there are levels, which is logarithmic. So pseudo-linear runtime complexity. So let us talk about the basic idea behind quicksort. And this idea is that we work with so-called pivot elements. So we have a list here, something like 3, 1, 6, 7, 2, 8, 4, 5, something like that. And what we do then is we pick a so-called pivot element, usually the first one or the last one. It has to be a specific one, right? Like always the last one, for example. And we pick this pivot element and arrange all the other elements so that the larger elements are on the right side and the smaller elements are on the left side. So in this case, it would be 3, 1, 2, 4, 5, 6, 7, 8. Notice that the order of these numbers stays the same. So 3, 1, 2, and 4 are still in the same order, even though 6, 7, and 8 are shifted to the right. The order of the individual elements stays the same. The only thing that we change is the 5. So the 5 has to be before all the values that are larger and after all the values that are smaller, but we don't change any order. We don't change the order of these sublists left or right. This is also called a stable sorting algorithm if we maintain the order. So what we have in this case is we have this element and it's already in the right place. So since all the larger elements are to its right and all the smaller elements are to its left, it's already in the right place. So what we do then is we divide in order to conquer later on. So we split up into two lists here. And these two lists are 3, 1, 2, 4, and 6, 7, 8. And now we recursively repeat the process. So what we do is we pick the same pivot element here, the last one, and we arrange all these elements. Now in this case, it's easy because it's already the case. So we have 3, 1, 2, and 6, 7 are already where they belong. And then we do the same thing. If there were elements on the right, we would again split into two lists. This time we only have them to the left, which was not on purpose. I just made the list up while making this video here. So we split into this list and into this list, pick again a pivot element, this 2 here, this 7 here, and then we repeat the same process. So in this case, it would be 1, 2, 3. In this case, 6, 7. And then we split again. So this is still the pivot element. This is still the pivot element. And then we split up into two lists. This is what we always do. So we have the list of 1, the list of 3, the list of 6 here. And these are the elements. And if you look at it, we now have the complete list sorted. We have 1, 2, 3, 4, 5, 6, 7, and 8. And this is already conquered. We don't have to merge it in the same way that we do it for merge sort. We just have to split them up in the right manner, and we end up with a sorted list. So every time we use the pivot element to arrange the elements in the right order relative to the pivot element, then we split into two lists if necessary. So if this here was not 6, 7, 8, but 6, 8, 7, we would split into 6 and 7 into separate lists. Same way, if this wasn't the 4 here, but 8, 2, and this was the 4, we would put the 2 in the middle and split into two lists again. And we would then end up with a sorted list as well. So this is what quicksort basically does. Now, when it comes to the runtime complexity of the quicksort algorithm, this might be a little bit confusing because you can actually end up with quadratic time, which might be confusing because we're talking about divide and conquer. We're talking about the most efficient algorithm. So how can it be that it ends up with quadratic time? Now, usually it does not end up with quadratic time. This is just the case in the edge cases. Usually you have a pseudo-linear time as well, so n log n. And at the same time, also with smaller constants, if you were to analyze it exactly, the pseudocode, you would end up with smaller constants than merge sort on an average case. But the problem is that sometimes in edge cases, you'll end up with quadratic time. And we're going to talk about that in a second. But first of all, let's look at the runtime complexity in general. Now, what we do is we'll pick a pivot element, which is possible in constant time. And then we arrange all the elements relative to that pivot element. So what we do here is we arrange them, we compare them, which is possible in linear time, obviously. So we do this in linear time, in n, in big O of n. This is possible. And now, usually what we do is we split the problem size, we split it again, we split it again. And we can say that this is possible in somewhat similar to logarithmic time on average. Because again, we have the amount of levels. This is how many time we need to do this linear process, because again, we have smaller problem sizes, but more problems and so on. So usually you could say you end up with log n times a linear operation. But the problem is that there are certain edge cases in which this is not the case. For example, let's say we have a list that looks like that. We have 7, 5, 3, 2, 1 or something. This is the list that we want to sort, and the pivot element is always the right one. So what we do here in this case is we pick this pivot element, and essentially we already lost, because what we do here is we arrange everything according to this pivot element. So we have 1, 7, 5, 3, 2. This is the pivot element, so everything's on the right, and we split the list only on the right side. So we have 7, 5, 3, 2. What we do now is we pick this one as a pivot element. Oh, it's again the minimum value. So it's 2, 7, 5, 3. Okay. So what we do next is we split it up again. And you can see where this goes, because the pivot element is always the minimum value. So we don't really split, but we only remove one element, which is obviously quadratic, because this has to be done n times. And n times is quadratic time. Now, this is just the edge case. This is only the case if we have elements that are, if our pivot element is always the maximum or the minimum value, or at least most of the time the maximum or minimum value. Because the moment that we pick an element as a pivot element, which is an edge case, which is an outlier, which is the maximum or the minimum and extreme value, the moment we do that, we essentially don't split the list. We have the same list with one element less. And if we always just remove one element, you have a linear runtime complexity. However, if you have a random list, the chances are that you're probably not going to have these extreme values as your pivot element. You're usually going to have something that ends up kind of in the middle if you have a large random list. So the amount of levels that you're going to have will usually be logarithmic. So even though the worst case runtime complexity is n squared, which might be confusing, the average case runtime complexity is n log n, which is pseudo-linear, and it's more efficient than merge sort, because the constants that we usually don't care about when we describe asymptotic growth, but still the constants that make a difference in practical programming are smaller when it comes to quicksort. So this is definitely something that you prefer over merge sort. Now, last but not least, before we end this video, I want to mention that there are some hybrid sorting algorithms like timsort, for example, that combine sorting algorithms, and they can be considered more efficient than quicksort. For example, timsort is actually used by Python. So in Python, if you use the sort function, so if you have a list and you sort it with Python, you're using timsort, and timsort is essentially a hybrid, a combination of quicksort and insertion sort. So what it usually does is it sorts with quicksort, and once it notices that it has to deal with an edge case, for example, these edge cases that we talked about, like the pivot element I choose is always the maximum minimum value. Once it's noticing that this is the case, it switches to insertion sort, because insertion sort is more efficient in dealing with these edge cases. So we prefer the quadratic runtime of insertion sort. We prefer it over the runtime, over the quadratic runtime that we have in quicksort when we deal with these edge cases. But usually we use the pseudo-linear n log n runtime in order to sort the list. So if you get an ordinary list, you just sort it with quicksort. But once you notice, okay, this is an edge case where the pivot element is always the maximum minimum, or something that would end up in a quadratic runtime complexity when we use quicksort, we switch to insertion sort to make things more efficient, because insertion sort is just faster in these edge cases. Usually not, but in these edge cases, in these very rare edge cases, it is. So there are also combinations like timsort. I just wanted you to know that. So let us start with the basics. A graph is essentially just a, you could say, data structure, or essentially just a structure consisting of so-called vertices and edges. So you have a vertex here. This is a vertex, and this here is an edge. And an edge typically connects to vertices. in a simple graph, there is nothing such like an edge connecting a node or a vertex to itself. So essentially we're having vertices and edges, and these vertices are connected by edges, and you can also have a graph consisting of subgraphs that are not connected. So for example, here we would have a graph, and this is another graph, but if you say this whole thing is a graph, it's still one graph that is just not connected here. It's not interconnected. And you have many different properties that such a graph can have. For example, in this case here, we don't have any cycles, circles, or whatever. If I close this here, we have a cycle. Now it's an interconnected graph. Here we have another cycle. Cycle doesn't have to be length 3. You could also say this here is a cycle or circle. Actually, I think it's called cycle if you're having directions, if it's a directed graph, and it's called circle if you have none. If it's an undirected graph. However, as I said, we're not going to go too much into the details here because the focus on this tutorial series is not teaching you graph theory and discussing the different properties of graphs. We're going to use graphs to apply algorithms onto them because this is something that's very important. And we're briefly going to cover the other properties that a graph can have, and then we're going to get right into the algorithms. Now, this here is a simple undirected graph, and if we add directions to each connection here, it becomes a directed graph. So for example, this means that the connection is from this, let's say these are A, B, C, D, and so on. This means that we can go from B to C, but not from C to B. This is not possible. This is because it's directed. Of course, we can have a connection in both directions. This is not a problem. But in a directed graph, we always have a direction for each edge. We don't just say these are connected, because in an undirected graph, I can go from B to C, from C to B, and so on. And in a directed graph, this is not the case. So another property that we can have is having a weighted, so-called weighted graph. So in this case here, if this is A and this is B and this is C, going from A to B is equally efficient as going from A to C, because we don't have any weights here. Now, if I go ahead and say, okay, let's say this here, this connection here has the weight 2, and this connection here has the weight 8, for example, this changes. Now, it's not equally efficient to go from A to C as it is to go from A to B. And we define what efficiency means for us. For example, if we're talking about these numbers, meaning how hard it is to get to the point, or how much effort we need to do to take, or how much, I don't know, kilometers we need to go until we get there, we would want to minimize the numbers. So from A to C, we could say these are 2 kilometers and these are 8 kilometers, right? So going from A to C is definitely more efficient than going from A to B. However, if we say these numbers are how much money you can get on the way, or how much value you can get from A to B or from A to C, we want to maximize the numbers. So we define what efficient is. If we are talking about something that we want to keep small, like distance, we're talking about smaller numbers being more efficient, smaller weights being more efficient. And if we're talking about larger numbers, something that we want to maximize, for example, money, value, or people to talk with, clients to see while going from A to B, something like that, we definitely want to maximize these numbers. So this is one property that we can have. And one thing that's worthwhile to mention, or worth mentioning, is that if you don't have any cycles, if we don't have any circle cycles in a graph, it is called a tree. So if you have something like that, where essentially it goes on and on and on, and you don't have any cycles, which means you don't connect something. You cannot just go full circle here. This is called a tree. Now, this also looks like a typical tree, but for example, this here would also be a tree. This would actually even be a path, because a path is when you always only have one direction to go to, but now it would be a tree. Now it would also be a tree, because you can always pick a root node and then it's just a tree, you know, like binary trees. We're going to talk about these data structures, but essentially these are the basics that you need to know about graph theory, and now we're going to get into the searching algorithms. So let us start with the so-called breadth first search, which is BFS, and it's a little bit difficult to pronounce for a non-native speaker. But essentially what we're doing here is we're preferring breadth over depth. So breadth over depth, which means that when we're traversing this graph here, the sample graph that I prepared here, we're going to prefer this over that. And this means that the order of how we're going to discover the nodes is a different one. So for example, let's say A is our starting point. What we can do to now go ahead and find all these other nodes is we could just go ahead and, try to go to the edges, to these outer nodes here, and then, sooner or later we would return to, we would have all nodes covered. We could go ahead and just do anything, but essentially we want to have a structure in finding or traversing through the graph, finding all the other nodes. And what we can do with the BFS is essentially we're looking at all the neighbors first and then the neighbors of the neighbors before we go any deeper into the graph. So what we can do, of course, is we can start at A, go to B, and then instead of going to the next node that's connected to C, we could also go to D or E or whatever. But in BFS, what we do is we first look at all the neighbors at level 1, layer 1. Then we look at layer 2 and so on. So when we start at A, what we're doing here is we're looking at the neighbors, which is B and C. So we mark these. Let me pick another color here. We mark these as the neighbors now. So these are the selections. These are the two neighbors of our starting node. And then we process these. So we go to B. We have now found B. Then we mark the neighbors of B, which is D and E. But we still have C, which is the neighbor of A. So we prefer this one first. We discover C, then we mark its neighbor, G. Then we go ahead, we go back to B. Its neighbor was D and E, so we cover D. D's neighbor is E, which is already selected. Then we go to E, discover E. Then we go back, instead of going to F, we go to G, or actually we need to mark F as a neighbor of E. And now instead of processing or discovering F, we go to G, discover G, and then to F. This is one way in which you could do it in a breadth first search. So we're always looking at the layers. So look, this is the layer 0, so to say. Then we have these two connections here. These two nodes are the first layer. And then we have all these connections here. And these are the third layer. So we process those first. And then we have this connection here. And this is the last layer, the fourth layer. Or did I say? Yeah, it's 0, 1, 2. Okay, actually 3. So this is the third layer. And this is what BFS basically does. So now let's talk about the opposite or alternative approach here, which is the depth first search, the DFS, as you can see here. And the DFS is essentially the opposite thing. So we start at a certain starting point, and instead of looking at the neighbors first, we go as deep as possible. Now, of course, in order to get going, in order to start the process, we need to pick a neighbor of A, because we cannot just go to H, for example, because it's not connected. But instead of going to B and C, we just pick one of them, for example, B. And now we're not going to process the next neighbor of C, but we're going to go as deep as possible before we get back to C. So what we do is we go to B, and then we pick, for example, D. There's not just one right way. There are many ways. You could also go ahead and pick E, for example. So we have A, B, D. And then the next thing that we do is, of course, because we only have one chance, not chance, but one option here, we go to E, and then from E, we can either go back to a neighbor of A or deeper into the graph, so to say, and we're going to F, of course. Now we have no options left, so we recursively go back. This is like, going out of a recursion, basically returning. So we're going back to E, and you can see, okay, from E, I can access C. Then from C, I can either pick G or H, doesn't matter, let's pick G, and then I pick H. And then you can go back and see, okay, I came from G, go back, no options, no options, no options, and so on. We would recursively go back until we reach the starting point A. And this is the depth first search. And by the way, because I didn't mention it for the BFS, the BFS and the DFS have a runtime complexity that is referred to as big O of V plus E, which means that it's not only depending on the vertices, because that would be a little bit irrational here, because we can have, for example, 5 vertices, and they could be connected like that, or they could be connected like that. So the amount of edges is definitely important when it comes to the runtime complexity of this algorithm or of those algorithms. So the runtime complexity is depending on vertices and edges, and the amount of edges can vary radically because if you have 1,000 nodes, you can have a very high amount of edges, a very large amount of edges, or a very small amount of edges. So this is the runtime complexity. We're not going to analyze the whole code here because we did this with sorting algorithms already. You should now know how to analyze algorithms. But essentially, the breadth first search and the depth first search have a runtime complexity of V plus E, so vertices plus edges. Whereas this is the amount of vertices and the amount of edges, of course. So let us talk about this algorithm here. And as you can see, we're dealing with a weighted graph. And weighted is important here because if it was not weighted, we could just go ahead and use a BFS, a breadth first search, in order to find the shortest path from A to any other node. Because if you don't have any weights, these blue numbers here, finding the shortest path is very simple. You just look at the neighbors, you go one layer further until you get to the node, and then you know a bunch of shortest paths, so to say. But since we're dealing with weights here, this is not applicable because the shortest path in a BFS from A to F would just be go to F directly because it's a neighbor. But as you can see, this has a cost of 3 here. And if we go first to B and then to F, so A to B to F, we have a cost of 1 plus 1, which is 2. So going from A to B and then to F is more efficient than going from A to F directly. So we can say these numbers here are the cost. So A to B has a cost of 1. We could also say a distance of 1, whatever. And now we want to find the shortest path from A to any other node. This is what a Dijkstra's algorithm does. We pick a starting node, in this case A, and applying the Dijkstra's algorithm, what we get is the shortest path from A to any other node. We don't have to select a specific target node. It just gives us all the shortest paths from A to B, from A to C, A to D, and so on. And what we need to do in order to apply the Dijkstra's algorithm is we need to set up a table here with one column which is called step, then a column for A, for B, for C, for D, for E, for F, and then 2 more columns. One is the selection and one is the previous node. Now the Dijkstra's algorithm is not complex at all. It's a very simple, very intuitive algorithm. It's easy to understand. We just need to fill out this table here in a very simple manner. So we choose a starting point, in this case A, and what we write down is with one step, how much distance is there from A to the other nodes. Now we can ignore this column here because A to A is 0 or nothing actually. We cannot say 0 because otherwise we would have to select it. Or we could say with 0 steps it's 0, so select it and so on. But essentially what we do is we write down the cost of going from A to all the other nodes using one step. One step meaning that we can use one edge. So in this case, from A to B, it's 1. From A to C, it's infinite because I don't have a direct connection between A and C, but I only have one step, so I cannot go A, B, C. I have to go directly there, and this is not possible, so we're going to say infinite. From A to D, it's the same thing. And from A to E, I have a cost of 5. And from A to F, I have a cost of 3. Now, the simple thing here that we need to do in the Dijkstra's algorithm is we just select the smallest value. Very trivial. The smallest value that we have here is 1. It's the connection from A to B. And then what we do is we just say, okay, we select B and we write down where we got, from where we got to B. So in this case, A was the previous node. So we got from A to B, and this is the selection. Now the next step is looking at 2 steps. So now we're looking at how much does it cost to get to a certain node using 2 steps. And we're not looking at all the 2 steps possible. We're not going to see or to check what is the cost from A to E and then to D, or from A to E and then to C, or from A to F and then to B, and so on. We're just going to look one more step from the node that we selected. So we selected B, and now the only thing that we need to do is what can I reach using one more step from B? And then of course we need to add the cost here. So in this case, we could go ahead. B is now dead. We don't care about B and we don't care about A. We ignore these 2. And we now ask, okay, how much does it cost to go from B to C? It costs 8. So going from A to C costs 1 plus 8 when we go through B. So we write down 9. So it's 1 plus 8, it's 9. And then the next thing is going from A to D. Going from A to D is 1 plus 7, so we have a cost of 8. Now going from A to E is the same with one step as it is with two steps, because we have 1 or plus 4 or 5 directly, so it's still 5. We don't change anything here. And then going from A to F is a cost of 2, because now instead of going directly, which costs 3, we can go A, B, F, and this has a cost of 2. Again, we pick the smallest number, which is F, or the smallest cost. And then we say, okay, we selected F, but we selected it from B. We didn't select it from A directly. This is important. We selected it from B. Then we say 3 steps. We ignore B, F, and A, so we only care about C, D, E. And what we do now is we ask, okay, from F going to E takes a cost of 2. So 2 plus 2 is 4, which is less than 5. Going from F to C is not really really possible. We cannot just go ahead and find a shorter path to C. So what we do is we just apply that 9. It's still the shortest path that we know. And from F to D is also not possible, so we just do it like that. What we do then is we select E again, we select E from F, and then we start the next row. And now we look from E, I can access C using a cost of 3, which of course is less than 9 because 4 that we already have. So you need to think about it this way. This here means that we can go from A to E with a distance of 4, with a cost of 4. This is obviously the case if we go that, and that. 1, 1, 2. This is a cost of 4. And now, additionally, I can go from E to C using an additional cost of 3. So this is essentially 7. And to D, I have to add 5. In order to go from E to D, I have to add 5. 4 plus 5 is 9, which is larger than 8, so we don't change that. We just copy the 8 here. And you can see that the next shortest thing is, or the next smallest number is C. So we select C, but we select C from E. And then we have 5 steps. Now we're looking at C. From C, I can access D with a cost of 3, which is 7 plus 3 is 10. So it's less, it's larger than 8. So 8 is actually the smallest number, but, and this is now tricky, or not tricky, but you need to think about this. We're not accessing, we're selecting D, but we're not accessing D from C, because accessing it from C would have a cost of 10. So we need to ask, when was the time where I got the cost of 8 the first time? So here I got the cost of 8, and I got it from B. I could access 1 and 7. 1 plus 7. So I actually access D from B. And now we can see the shortest paths in this table here. So let's try to find the shortest path from A to E, for example. If I want to find the shortest path from A to E, I just go to the column where I selected E and then go back. So I can see, okay, I have to go to F, back to F essentially, then to B, and then to A. So A, B, F, E is the shortest path. We can see it right here. If I want to know the shortest path from A to C, I just go C. Okay, it's E, F, B, A. So it's A, B, F, E, C. A, B, F, E, C. A, B, F, E, C. This is the shortest path. And now if we want to have a little bit a better overview, so to say, what we do is we just draw the graph that we can see here. So we can just use these selections in previous, this data here essentially, we can use it to graph, to draw a new graph here. Starting at A, we go to B, obviously, and this has a cost of 1. From B, we go to F, and this has a cost of 2, so we add 1. Then we go from F to E, and this has a cost of 4, so we add 2. Then we go from E to C, which has a cost of 7, so 3 more. And then we go from B to D, which means that D is actually here. And this has a cost of 8. So this is a 7. Because up until B we needed 1. And then this is essentially the graph that shows us the shortest path. As you can see, it's similar to the graph above, but all the edges that we're not using to find the shortest paths are just removed. And now we have only the most efficient edges, so to say. Now, if I want to go to D, I see I have to go to B first and then to D. There's only one path. This is essentially a tree. And it's the you could say a Dijkstra tree or whatever. It's just a graph showing you the shortest paths to each node from A. And you can now use this to, find the shortest path essentially. This is a very simple and a very efficient algorithm to find the shortest path from any starting point to any other point in the graph. So let's start looking at this graph here, and don't be confused. Yes, it's a little bit larger than the graphs that we looked at before, but it's, the Kruskal algorithm, it's very simple. So we need a large graph to show what it does. And it's, again, a weighted graph here. So it has to be weighted, of course, because we're looking at a minimum or a maximum spanning tree. And a spanning tree is essentially just choosing all the edges that cover all nodes. So essentially we want to end up with a bunch of edges that cover all nodes so that all nodes are interconnected and we can get to every node with a minimum amount of cost or a maximum amount of benefit, whatever, in whatever way you interpret these numbers. So if these numbers represent the amount of money you get when you go there, you want to maximize it. If they represent the distance or the amount of money you have to spend to get there, the cost, you want to minimize them. So we want to end up with a tree where we can remove all the edges that we don't care about, all the edges that are inefficient, and we want to end up with a minimum spanning tree, so to say. Now, for example, what we could do without applying the Kruskal algorithm, we can just go ahead, for example, and delete this edge here, because obviously we don't lose any nodes because of that, and it's a very high cost edge, so to say. We cannot remove this edge here, even though it has a cost of 8, because there's no other connection to this node. So you get the idea of what we're looking at. And the Kruskal algorithm is actually very simple. If we're looking for a minimum spanning tree, we're just looking at the minimum cost edges and choosing those edges as long as they don't build any circles. So for example, if I were to choose the 1 here and to choose the 2 here, I could not choose the 3 anymore because it would close a circle. It would go ahead and close a circle. And we don't want to have any cycles, circles, or whatever in here. So what we need to do here is we just start with the smallest values. So 1, for example, or not, for example, 1 in this case, and we choose this edge. So we have one edge already that we've chosen, and we don't find any other ones here. So we proceed with 2s, and we mark all the 2s. So this is a 2. We select this edge. Let me just make this a little bit thicker here. Maybe I can use a line tool like that. Yes. So we choose this one. We choose this one first, of course. Then we also choose this one and this one and this one. And of course, this one. All the 2s are just being chosen. And then we have no 2s left. So we proceed with the 3. We choose this 3 here. We choose this 3 here. As we already said, we're not going to choose this 3 here because it closes a circle. We're not interested in that because think about it, we're not getting any benefit. We already have this node covered, this node covered, this node covered, sorry. Adding this edge doesn't give us any benefits. It just connects these 2 nodes, but they're already in our spanning tree, so we don't care about them. Then we choose this edge and the 3s are done. We proceed with the 4. We choose the 4 here. It doesn't close a circle. We choose the 4 here. It doesn't close a circle. And that's essentially it. Then we go to 5. We don't choose this 5 here because it closes a circle. If we choose this 5 here, you can see that this circle here is closed, so we don't choose it. We choose this 5, however, because it does not close a circle. And it's important to connect these 2 graphs. This would close a circle. This would not close a circle, so we use it. We choose it. Then we proceed with the 6. We don't choose this 6 because it closes a circle. We don't choose this 6 because it closes a circle. And we don't choose this 6 because it also closes a circle. So we don't choose any 6 here. We have 7, this 7 here closes a circle, this 7 here closes a circle, so we don't choose it. And then we're only left with the 8s, this 8 closes a circle, and as I already mentioned, this 8 here is mandatory. Even if it was 1,000, we would have to choose it because there's no other way we can include this note. And this is the result essentially. If I didn't miss anything, every node should be covered. And we could now go ahead, I'm not going to do it completely, but we can now go ahead and rewrite or redraw this graph here by having all the nodes that we just had, all the same nodes, but now we're just going to delete the edges. So, or now we're just deleting the edges. We're just going ahead and saying, okay, we only have this edge, this edge, this edge, this edge. It's still connected, but it's a minimum spanning tree. So we don't need this edge here, and so on. Actually, an easier way would just be to delete the edges. So we could just go ahead and let me choose the delete tool here. Could just go ahead and delete all these edges here, and we would end up with the minimum spanning tree for this graph. So all nodes that are not, all edges that are not selected are deleted, and we would end up with this minimum spanning tree here, this one too, where all the nodes are connected, interconnected with the minimum amount of cost. We can do the same thing for the maximum amount of cost. The only thing that we need to do then is we need to start with 8 and go and decrease the value with each iteration, so to say. This is the basic Kruskal's algorithm. Now, before we actually get into linked lists, let's talk about arrays real quick, because I didn't want to make a full video on arrays. They're pretty simple, but we still should mention their runtime complexity, and also it's important in order to compare it to linked lists and so on. An array is essentially just, a data structure that reserves a certain amount of slots, positions, whatever. This, for example, is an array of size 8. And in an array, we have memory addresses that are neighboring. So in the RAM, we reserve a certain block. We say, okay, I want 1 byte or 1 whatever. We're not going to get into the hardware details here. We're just saying, I want this block of memory, and then we have these memory addresses. So we have 0x1, 0x2, and so on, up until 0x8, for example. And whenever I want to access an element, I know where it is. I don't have to go through all the other elements. I can just go ahead and say, okay, I want to access the 6th element here. So what I do is I calculate the position, in this case 0x6, and then I can directly access it. I don't have to do anything, so this can be done in constant time. Accessing an element of an array or in an array is done in constant time. It's very efficient. I just have to calculate the address because they're all in the same block. It's very simple. I know the exact address of for each position. I can calculate it in constant time, and this is why I can access an element in constant time in an array. In the same way, I can delete an element in constant time, because what do I have to do? I have to find the position, can be done in constant time, and then delete the element or insert the element. Whatever I want to do in an array, it's possible in constant time. The only thing I cannot do in constant time, of course, is finding an element, because for finding an element, I have to go through the whole list. And in the worst case, I find it in the last index or not at all. So this is obviously done in linear time, big O of n. And of course, more complex operations like sorting, we already talked about. Sorting is done in the best case, or not best case, but average case of n log n time. So big O of n log n if we want to sort. But the essential operations of access, insert, and delete are done in constant time in arrays. Now this works differently for linked lists, because linked lists allow for a so-called dynamic sizing. The structure allows for dynamic sizing, and this is because linked lists are composed of so-called nodes that are independent from each other. So we have the node A here, for example. This is the value A, or it could be 10 or 6 or whatever. And then we have a pointer here pointing somewhere. And if this is the only element of the linked list, it would be pointing to null, so indicating that the list reached the end, or this is the last element, and at the same time the first element. But usually what we do is we point to the next node, and this node has also a value, let's say B, and it points to another node. And this has another value, for example C, could also be X, doesn't matter. And so on until we get to null again, which indicates that the list has reached the end. So this is the last node called the tail, and this is the head. So the first node is the head. Nothing is pointing to the head, at least in the singly linked list. nothing is pointing to the head. And this is the structure of a linked list. Now the good thing is, or the reason why it's dynamically sized is, these nodes are completely independent from each other. Now remember, in arrays, when we allocate memory space, we say allocate this amount of space here, and all the elements are neighbors. So if I want to have the sixth element, what I do is I just calculate the position or the memory address for the sixth element, because I allocated a block and I know where the starting point is and I know where I want to go. So the only thing I need to do is I need to calculate the memory address. This is not possible for linked lists because all these nodes allocated memory space independently from each other. So if I allocate memory space for this node here, I have a certain memory address, let's say 0xf2 for example. Then I allocate space for this one. This could be at a completely different address like 0x3d, and this could be at 0x12, whatever. Because whenever I create a node, I allocate memory space for that node. I don't care about all the other nodes because they are independent from each other. I just allocate space, memory space for this particular node, and then I adjust the pointers. Now, yes, they're interconnected in the big picture because we're dealing with a linked list and A is pointing to B, B is pointing to C, and so on. But this is just the pointer. The pointer, yes, we have an element that is a pointer, and this pointer points to B. The pointer of B points to C, and so on. Sure, but in the end, these are independent elements. They have completely, not random, but independent memory addresses. So I cannot just go ahead and say calculate the address for the third element. I can only go to the third element either by accident or by going through all the elements. So if I want to go to index 2 or to the third element, what I do is I go to the first element, to the head, and go to its pointer. Look at its pointer, go to next element, increase the counter by 1. Now I'm at the second element, index 1 or second element, whatever. Then I go one further, and now I reach the third element. So I cannot just go ahead and calculate the address. I cannot access any element in constant time because I cannot just go ahead and calculate the memory address. I cannot say I want to go to the element at index 400 because if I want to go there, I have to go through 400 pointers. I cannot just reason my way through the memory address or to the memory address because there is no structure in there. These are all independent nodes. So what we need to do is we need to go through all the pointers, and this means we have a linear runtime complexity worst case, because in the worst case, to access an element, we need to go through all the other elements. So through n elements, through n nodes, through n pointers, so to say. So accessing is done in linear time. Accessing is done in linear time. Which is big O of n, in the worst case, of course. Now, of course, accessing the head can be done in constant time. No shit. Accessing the second element can also be done in constant time. Accessing any particular element can be done in a constant time. But accessing any element is done in linear time because it always depends where this element is. Whereas in arrays, I can just, no matter which element, the calculation is the same. And it takes the same amount of time. So this is also true, of course, for inserting elements and deleting elements, because if I want to insert an element in between B and C, I of course need to go to the address and to this address and adjust the pointers. So this is a little bit of a contradiction here, because the actual act of inserting can be done in constant time. Because if I know the memory address of B, if I know the memory address of C, the act of adding a new node here, X, and adjusting its pointers so that this pointer points to C, and we delete this pointer and it points to X, this can be done in constant time. So in a sense, when you look up inserting and deleting in linked lists, you will oftentimes see that it's possible in constant time, which is true because the inserting and the deleting of nodes and the readjusting of pointers can be done in constant time, obviously, because it's the same operation no matter where you are. But finding the addresses where you need to do it, this takes linear time, as we already saw. So in total, it would still be linear time, unless you have some iterator that allows you to access the individual memory addresses in constant time. Then, of course, you can insert and delete in constant time. But practically speaking, it's done in linear time. And of course, finding elements is also done in linear time because you have to go through all the elements in the worst case to find an element. So this is the structure of a linked list. Adding an element, appending an element, you just create a new node, allocate a new memory space. In this case, it could be something like 0x5f. And then what I do is I readjust the pointer here. So I let C point to D and D point to null. And of course, I can also add, as we already said, a new element here, x pointing to C, and B pointing to X, readjusting this pointer. And this is how you insert, delete, and link lists. So the size increases because the memory address, we're not reserving, we're not allocating a fixed sized memory block. So adding elements is not a problem because as long as there's memory in general that we can allocate, we can add as many elements as we want, because we don't have this static data structure. We have a dynamic data structure that's all over the place, but connected by these pointers. Now, one thing that I want to briefly mention at the end of this video is that there are also doubly linked lists, which essentially means that we don't have only a single connection, only a single pointer, linked list, of course. We don't have just a single pointer, but we have an element that has three things. It has a value in the middle, it has a previous pointer, and a next element pointer. So this is a doubly linked node, so to say, and then we would have the next node here, B, and this B would point to the next node as well, but also to the previous node. So we have a double connection here. Of course, the head element points to null, and the last element, if we have a C here, let's see, this is C, points to B. Of course, it also points to null since it's the last element. The runtime complexity all remains the same for all the operations, inserting, deleting, accessing, finding, has still the same runtime complexity. We don't change anything here. But of course, it may be a little bit more comfortable to navigate to the previous element, or to be able to navigate to the previous element as well. So this is just the one thing that I wanted to mention at the end of this video. So let's talk about the basic idea behind a stack. A stack is essentially the exact thing that the name suggests, a stack of data units. So you can imagine a stack to be something like this, where we have a lot of packages, a lot of data units, a lot of whatever this is, stacked on top of each other. And this essentially means that we have a stack of data. Now, what we can do with this stack of data is we can push new data on top of it. So we can go ahead, create a new data unit here, a new package, and we can push it on top of the stack. And we can also go ahead and pop the element at the top. So we can go ahead and say, okay, take the element at the top of the stack and process it. And alternatively, we can also go ahead and just peek at the stack. I'm not sure. I think peek with double E, not with EA, because peek would be like the top point of something. However, this is what you can do with the stack. You can push data on top of it. You can pop the last element from the stack out of the stack and then process it. Now, this means that a stack operates in a so-called first in, last out, or last in, first out principle. So philo or LIFO or LIFO, whatever. This essentially means that what enters the stack first leaves it last, and what enters the stack last leaves it first, which of course makes sense, because what we do is when we push an element on top of the stack, so let's say this is a red box here, what we do is we essentially put it on top of the stack. So now the top element is this red box here, and when we pop the element, what we get is the top element, so the red box here. So usually we're going to talk about the queue data structure in the next video, and priority queues as well. But essentially, a queue, an ordinary queue, works in a different way. You put in an element, and what gets into this queue first leaves the queue first as well. With a stack, that is not the case. What enters first leaves last, and what enters last leaves first. Now, when is this important? How can this be used? Basically, when we're talking about function calls, for example, or recursion. Now, these are not the only use cases for recursion. These are not the only use cases for the stack data structure, but these are the, I would say, main or most common uses of stacks. Because what we do when we call a function, on a low level of programming is we save, once the function is finished, where do we return? So for example, you have some code here, some lines of code, and then we have a function call. And what we do is we navigate to that function, execute that function. So this is some other call here. And maybe inside of that function, we call another function, function2. And this function calls another function, or not calls another function, but has another code to be executed and so on. And once this code is executed, we have to go back to this point here. Once this code is executed, we have to go back to this point here and so on. So what we can do is we can essentially build a stack data structure. And the first thing that we add is the return point where we have to go to. So we have some code and then we call the function the first time. So what we do is we say, okay, the first layer here is the first function call. So return to that first function call once everything is done. So in the second thing here, we have another function call. So we say, okay, the next function call is function2, return to this one once it's executed. And then maybe you have function3 and so on until you get to the top element, until you have no other function calls. And what you do then is you execute the code, and then what you do is you pop the top element because you don't want to return to this function immediately. What you want to do is you want to return to the last function called, to the last point in your code where you call the function. And you're going to return to that, then you're going to execute it, then this element is gone, of course, because when you pop an element, it's gone. It's no longer in the stack. Then you do the same thing for function 2, function 1, and then the code proceeds. So this is what basically how the stack is used. The same way, it is the same way for recursion, essentially, because when you call recursively, you have you always enter in the stack where you want to return to once the recursion is done, once this signal processing is done. And this is why we get why we use stacks in order to process function calls and recursions. And this is also the reason why we get this famous error called stack overflow error. Now, this is not only a platform where you can get help with your code, this is also an exception that you can get in programming, which means that the stack that you have is too full. You added too many things onto the stack and there's no way to put more things into the stack, so you get a stack overflow error, or just a stack overflow. And this happens when you have too many function calls. For example, if I have a function that calls, in its code, it calls function 2 here, and function 2 just goes ahead and calls function again, you have all this has to be put into the stack. So what you do is you say, okay, return to function 2 call, return to function call, return to function 2 call, and so on. And sooner or later, the stack will be full. In the same way, recursion, if you have a function that is just this function here, and the only thing it does is calling itself, you're going to call, this function is going to call itself infinitely many times, or not infinitely many times, but as many times, or so many times until this stack is full, basically, and overflowing. And this is the reason why you get stack overflow error once you have too many recursions or too many function calls, because the stack is too full and you cannot put in more entry points for function calls or recursive calls. Now, when it comes to the runtime complexity of the stack, that's pretty simple because the only two operations that we essentially have is pushing and popping. And these are very simple operations because pushing is essentially just looking at the active position, at the position that we are at right now in the stack. And the only thing that we need to do is to push an element. That's why it's done in constant time. Same for popping. The only thing that we need to do is we need to take the active element and pop it out of the list and reshift the index, reshift the pointer that points to the active element. So essentially constant time as well. Then we also have the peak operation, and the peak operation is also, of course, possible in constant time because we just have to look at the element. Peak basically means you're looking at the top element without removing it. So it's the same as pop, just that the element stays inside of the stack. So you don't remove it, you just look at it. Yeah, and essentially you can also go ahead, which you would usually not really do in a stack because that's not really what a stack is used for, but essentially you could go ahead and access a certain position or find a certain element. So if you have a stack of values here, A, B, C, D, E, you could just go ahead and say, okay, is there a D inside of my stack or something like that? And you can go look for that value, but what you need to do for that is essentially pop all the elements out of out of the stack. In the same way, if you want to say, I want to have this particular position here, I want to access this particular position, you would need to pop all the elements before that. Similar to a linked list, this means that you need to go through all the elements that are before this element. And in the worst case, this is obviously a runtime complexity that is linear, because in the worst case, you have to go through all the elements until you get to the element that you're looking for. So these are the runtime complexities for a stack. So as I already mentioned in the introduction, a queue is very similar to a stack, but now we don't have the operations push and pop, but we have the operations enqueue and dequeue, which is essentially the same thing, but the difference is that we're not looking at the top position, but dequeue is looking at the last position and enqueue is looking at the first position. So it looks a little bit like a stack flipped on its side. We have this structure here, and these are the units here, the data units. And whenever we dequeue something, it gets out of the list from the end or from the tail, you could say. And whenever we enqueue something, it gets in front of the list in the first positions. Now, this of course means, as I already said in the introduction, that this is a first in, first out principle, or a last in, last out principle. Whatever enters the queue first leaves the queue first. So this means if I enter a red element, I'm going to put it here. Then I enter new elements. So here will be an extra element, and the red element, or actually not an extra element, we're going to push an element. So whenever we dequeue, enqueue, whatever, we're going to process this element here, and the red element, whenever we enqueue something new here, will be shifted to the right. So we're always essentially in a queue-like manner shifting the elements forward. So what enters first leaves first. This is a very simple principle, basically. Now, the runtime complexities obviously are the same as for the stack, because we have the same operations, just looking at different addresses. We don't need to do anything particular special here. The only thing we do is we push at the beginning and we pop at the end. So it's just another name for the same operation. So enqueuing can be done obviously in constant time. Dequeuing can be done in constant time as well. Now, where are queues used? Essentially, they're used in all kinds of different application fields. I can tell you one example where we use them on this particular channel. One of the first videos that I made on this channel is called Threaded Port Scanner, where we're scanning ports using multi-threading. And what we did there, because we had thousands of ports to be scanned, and we have like 500 threads running or 50 threads running, whatever, and all these threads are going to scan the ports. And now what you can do, of course, is you can define a counter variable that says, okay, counter equals 0, and whenever a thread wants to check a port, what we do is we increase counter by 1 and process the number. But the problem is we have 50 threads accessing this variable at the same time, so sometimes it will happen that 3 threads at the same time decide to increase the number, then we skip 3 ports, or sometimes we're not going to increase at the right moment, and 3 or 4 threads are going to scan the same port at the same time, which does not make a lot of sense using this variable accessed by 50 threads or something, let alone by 100 threads. So what we can do, and what we did in the tutorial, is use a queue structure where we essentially had all these ports. So we just entered all the ports, and then we said, okay, 1, 2, 3, 4, and so on up until any number of ports that we cared about, for example, 1024 or something. And what we did then is each thread, if they wanted to scan a port, had to dequeue an element. So thread 1, for example, thread 2, thread 3. Thread 1 was faster than the other 2 and wanted to process an element, so it dequeued the 1. It processes the 1 now. There is no chance 2 or 3 are going to process 1 as well, because they also have to dequeue an element from the queue. And once 1 is dequeued, we cannot dequeue it a second time unless it's in there a second time, of course. So it's going to get 2. And even if they access the queue at the same time, they're not going to get the same element, because you have to dequeue it, and you cannot dequeue something that's not there. So this is one application that I personally already did. I used queues already in Python for developing a threaded port scanner. Now then we also have something called the priority queue. And the priority queue is not operating using the first in, first out principle, nor is it operating using the first in, last out principle. So the priority queue works differently in a little bit more complex way, which is using priorities. So we have still the same methods, enqueue and dequeue, but now we're not necessarily always dequeuing or essentially we are dequeuing at the last position, so at the end of the priority queue, but we're not enqueuing them necessarily at the beginning. So what we have is, imagine it's something like that. You have data packages here, and these data packages not only have a value, but they also have a priority. So you have, for example, the value up here, which is, I don't know, A, X, Y, Z, whatever. And then you have priorities here. So for example, a higher priority could mean that it's more important. So a higher number could mean that it's more important. So the Z could be priority 5, the Y could be priority 3, and these two can be priority 1, which means that whenever we process something, the highest priority gets dequeued first. And you can say 5 means it's the highest priority. You could also say 1 is the highest priority, whatever you want. But let's say the higher the number, the higher the priority. And in this case, Z would then be the highest priority. So when we call the dequeue method, we're not necessarily just calling, or essentially we are necessarily just popping out the last element, but the last element will always be the one with the highest priority. So when we enqueue a new data package, we're not just going to put it at the beginning here, we're going to ask what priority it has, because we can go ahead and say, if we want to enqueue something like, I don't know, H, and H has a priority of 4, what we need to do is we cannot just go ahead and put it here. We would have to put it in here, in between 3 and 5, in between Y and Z. This is where it belongs. Now, the idea is quite simple. It's not that hard, but the question is, how can you implement that in an efficient way? Because of course, what you could do is you could use a linked list, of course, and just enter it here. Say, okay, this is H with priority 4, and then use a sorting algorithm, or use some sort of getting it there, or scanning through all the elements and determining the position, iterating through the whole list. And in the worst case, you would need something like n or nlog n. You would have n or nlog n runtime complexity, which is not a good thing because you would have to go through the whole list and find the position and then enter it there. The question is, how can you implement a priority queue in an efficient way? And this is the topic of the next video, because the answer to this is the so-called heap data structure that we're going to talk about in the next video. Because with the heap data structure, dequeuing and enqueuing are possible in logarithmic time, so in big O of log n. And we're going to talk about how this works in the next video. So let's talk about the heap data structure. Now what you can see here on the left is a binary tree. And a binary tree is essentially just a graph without cycles where each node has 2 children. So we have one node A here, and it has a left child and it has a right child. That's essentially what it means to be a binary tree. Now, of course, sometimes you're only going to have a left child because you don't have an additional element that you want to add to the list. So you have only a left child, and then you have basically null, which is, you could say null is the right child. Whatever, this is a binary tree, but this binary tree is special because it fulfills the so-called heap property. And the heap property depends on what kind of heap we're looking at. In this case, we're looking at a max heap, and this means that every child has to be smaller than its parent. So each parent node has to be larger than all of its childs. So 17 is larger than 2 and 7, 19 is larger than 17 and 3, 100 is larger than 19 and 36, 36 is larger than 25 and 1. So in this case, the heap property of a max heap is fulfilled. This is essentially what you always want to maintain in a heap. You also have the min heap, for example, where it's the other way around. So the heap property here is that the parent is always smaller than its children. So you could have something like 5, and then you have 16 and 28. Well, that's not an 8, 28. And then here you have something even larger, so 50 and 60, for example, whatever. But notice that unlike a data structure that we're going to learn in the future, or learn about in the future, the binary search tree, it doesn't matter if the left node is larger than the right node, or the left node is, there's no specific order. The only thing that we want is that the parent is always larger than its children. This is in a max heap at least, or the other way around in a min heap. We don't care about the left child being larger or smaller than the right child. The only thing we want is that this is the largest element, then these are the 2 largest elements after that, and so on. So this is the basic heap property in a max heap, and in a min heap, it's the other way around. Now let us go back to the idea of a priority queue. What we wanted out of a priority queue is that elements get processed based on their priority. So we had a bunch of elements and they had a priority of 1, 2, 3, 4, 5, 10, 1,000, whatever. And we can say the lowest number means the highest priority, or the largest number means it's the highest priority. And then what we wanted to do is we want to enqueue elements. They get sorted into the list in logarithmic time. This was our goal. And we also wanted to dequeue the element with the highest priority first. Now, we talked about how we could do that with a linked list, but the sorting and the accessing would only be done in linear time, or possible in linear or pseudo-linear time. So what we need to do is, or what we wanted to do is, we wanted to find a logarithmic way. Now, let's go to our heap here and look at it. Now, what we have here at the root in a max heap is always the largest element, and the root node can be accessed in constant time since it's always the same address. If you think about this tree as having all these childs, all these positions in fixed memory addresses, you can say that the root node is always the largest element. If the heap property is satisfied, the root node will always be the largest element. And if we say that the largest element is the largest priority, the highest priority, we can say that the element that has to be dequeued next is always at the root node. So in this case, we could always just pop this out basically, and we could process the root node. Now this would be deleting an element, and we're going to talk about that in a second, how this would work and why this is possible in logarithmic time. But let's talk about inserting first, because in this case, it's very easy to see that the root element is always going to be the largest one, but this part down here doesn't look really sorted. We have 19, 36, 3, 1, 2, all over the place. So let's think about how we can insert elements into this heap data structure in logarithmic time without violating the heap property. Now, what we would do for that is we would just go ahead and append the new element at the end of this heap data structure. And at the end means that we fill this tree data structure up from left to right. We don't just add it somewhere here, but the next element, whatever it is, will be the left child of this, the next free place. If you look at it like that, this is the first position, then we have 2, 3, 4, 5, 6, 7, 8, 9, and so on. These are the positions, so this would be the next one that's free. So whatever element we add here, let's say we add the number 92 here, whenever we add a new element, we just append it onto the next next free position here. So what we do is we say, okay, this is 92 here, and the problem is now the heap property is violated. So what we do in order to restore it, in order to satisfy it again, is we perform a so-called heapify up operation, heapify up, which essentially means that we just go to this element here and compare it to its parent. So we say, okay, 3 is less than 92. That violates the heap property. So what I'm going to do is I'm going to change it by swapping these two nodes. Now let me delete them real quick. So we're swapping 92 and 3. So we have 92 here, and 3 is the left child of 92. And what we have now is we have the next check, because now what we have to do is we have to compare it to its parent again. We can see 19 is less than 92. So what we do is we perform another swap here, and we swap 92 with 19. 92 and 19. So we have 92 here and 19 here. By the way, we don't need to check for that 17, because since 92 was already larger than 19 and 19 was the parent of 17 and thus larger than 17, we don't need to compare 92 to 17. It's going to be automatically larger than 17. Now what we have to do is we have to compare it to 100, but 100 is larger than 92, so it's done, and we have the heap property satisfied again. Now, this is possible, obviously, in logarithmic time, because again, we have the same thing that we have with merge sort and all that. We have the amount of levels, so we have 1, 2, 3, 4 levels, and the amount of levels is the logarithm of base 2 of the amount of elements. So the amount of levels is logarithmic based on the amount of elements, and because we don't need to compare more than the amount or more times than the amount of levels, we have to do the comparisons a maximum amount of time as there are levels. Well, this was not an English sentence. What we need to do is we need to start at the bottom, and in the worst case, we need to compare it to all the elements through all these levels, to all its parents essentially, until we get to the root node. So the worst case is we go through all the levels, but the amount of levels is logarithmic. The comparison itself is constant. Thus, the process of inserting is logarithmic as well. So heapify up and inserting are a logarithmic operation. So now we know how to enqueue elements in logarithmic time. We know how to put new elements into this heap data structure, into this priority queue. But we also need to find a way to pop out the elements, to process the elements, because we already set 100 here, or the root node is always going to be the next element to be processed. The highest value will be at the root node. In a min heap, it's going to be the lowest value, depending on what kind of priority you're interested in. And we want to process it, but then after processing it, you need to remove it from the heap data structure. And if we just remove 100, you have an empty root node and no longer any tree. You don't have a tree anymore. And if you just shift around some things, you maybe violate the heap property. So we need to find a way to pop out an element and restructure the tree so that it fulfills the heap property again in logarithmic time. Because then we have a method to insert an element into a data structure based on its priority in logarithmic time. And we can also pop out the largest element, so the most important element, and restructure the tree again so that it works the next time in logarithmic time as well. So everything that we want to do in the priority queue, enqueuing, dequeuing, can be done in logarithmic time once we figure out how to do that. So what we do here is we essentially just delete the root node and process it. So we pop it out. We say, okay, 100 is the element, and then in your programming code, you do whatever you want with it. You say, I don't know, do some calculations with it, but then we remove it from the tree. And what we do instead, or what we do after that, is we take the last element here. It doesn't have to be the smallest, but it's going to be the last element in the tree. We said we fill it up from left to right. So the most right element of the last level, of the last row, we take it and replace the root node by this value. So I'm going to redraw the tree here without the circles. So we have 3, 92, 36, 17, 19, 25, 1, 2, and 7. This is the now the new tree. The 100 is out of the tree. And what we need to do now is, you can obviously see that the heap property is violated because there is a 3, a very small, one of the smallest elements is at the root node. So what we want to do now is we want to perform a so-called heapify down. So this is the opposite of the heapify up operation, the heapify down operation. And what we do here is we just take this element here, this root element, and we compare it to the largest of its children. So in this case, 92, because 92 is larger than 36. And we compare it to 92. And if 92 is larger than 3, we're going to swap positions. So in this case, it is. And because of that, we're going to swap the positions of 92 and 3. And we will get one level down, so 92 and 3. And now you can see why we picked the larger element, because if I was to swap it with 36, which would also be fine because 36 is larger than 3, we would have 36 as a root node here, which is above 92, even though it's smaller than 92. So you always want to swap it with a larger element, or compare it with a larger element to the larger element. Now in this case, again, we have the 3 here, and we compare it to 19 because 19 is larger than 17. We can see 3 is less than 19. So what we do again is we swap their positions, and we say 19 and 3 change places. So we have 19 up here and 3 down here. And as you can see, in logarithmic time, same logic as with inserting or heapify up. In logarithmic time, we have restored the heap property. We're again satisfying the heap property here. And this can be done in logarithmic time again because we have a logarithmic amount of levels. We have log2, a maximum of log2, log base 2 of the amount of elements levels. This is the amount of levels that we can have as a maximum. And because of that, the amount of operations that we need to do is logarithmic. And thus the heapify down and the whole deleting or popping operation, the whole dequeuing operation can be done in logarithmic time. Now, as the name already suggests, we have a binary tree here that has a certain additional property. And a binary tree is essentially just a tree where each node has 2 childs, which is the left child and the right child. And then these nodes, of course, have a left and a right child, and a left and a right child, until we get to the leaf nodes, where you essentially have no childs, or maybe you have one more and this one is a leaf node. And this is essentially what a binary tree is. And a binary search tree now adds a constraint to this, which is the following: that the left nodes, the nodes to the left, have always got to be smaller than this root node here. So we have, for example, the number 35 here. If we have a node to the left, this node has to be less or equal to 35. So we can say it's 27. Now, if we have a node to the left here, it has to be smaller than 27, for example, 15. Now, the thing is now, if we have a node to the right, it has to be larger than the parent node. So if we have a node to the right here, it has to be larger than 35, for example, 46. But if we have a right one here, it has to be larger than 27, but still, since it's to the left of 35, it has to be less than 35. So essentially, you can say it's something in between 27 and 35. So for example, 31. And this is the whole structure of the tree. So here we have less than 46, but still larger than 35. So for example, 37 and so on. This is the essential structure of a binary search tree, which essentially means that the middle element is, or not necessarily the middle element when it comes to the position, but the root node says that everything that's larger than the root node is going to be to the right, and everything that's smaller than the root node is going to be to the left. This is the center of attention, and this splits the list into two halves. Now, in this case, this tree is kind of balanced because we have 3 elements here, 2 elements here. It's not really unbalanced, but a binary search tree could also be something like 25, 22, 21, 4, and so on, and maybe just here you have 30 or something. So this is unbalanced, but it's still a binary search tree. A binary search tree doesn't have to be balanced, and it doesn't have to have the center element as a root node. So it could actually also be just a path like this one. This would also be a binary search tree, technically speaking. The only thing that we need to make sure is that each element has only smaller elements to the left and larger elements to the right. Now let's talk about why we even need binary search trees, why they're important, why they're beneficial to us. And the answer lies in the second word here, which is search. We talked about this in the last couple of videos where we said that the runtime complexity for most data structures to find something is linear. So to find an element, if we have an array of numbers here, which is not sorted, or a linked list, where you have a bunch of nodes pointing to the next node and so on, in order to find an element in here, you have a runtime complexity that is linear, worst case, and also average case, because you need to go through all these elements. Even if you don't have to go through all of them, you're not going to have a logarithmic runtime. You're going to have a linear runtime. Maybe you're going to have n divided by 2, but it's still linear because 1/2 is just a constant factor. Whatever it is, you will not end up with logarithmic runtime complexity. However, in binary search trees, this is not the case. On an average case, you're going to end up with a runtime complexity that is logarithmic, so theta of log n. Now, the worst case complexity still remains linear, and we're going to talk about why this is the case in a second, but in an average case, in a basic in a usual tree, you're going to have a logarithmic runtime complexity. And let's look at why this is the case. If you have a basic binary search tree, you always know where to go to. So let's extend this tree a little bit. 51, let's just add one more level here. We have 7, we have 19, we have, has to be less than 31, larger than 27, so that. Then this has to be less than 35, so 34. Then here we could have 36. Here we could have 41. Here we could have, it's not the most beautiful tree, I know, sorry. Then we could have 47, and then we could have 65 or something. So this is a binary search tree that is kind of balanced, that is actually totally balanced. And in this case, if you want to find, for example, the element 41, what you need to do is you just have to navigate through all these nodes. So what you do is you look at 35 and you're looking for 41. So 41 is the number we're looking for. And when we look at 35, we can know for sure in a binary tree, in a binary search tree, that this number, if it exists, is going to be to the right. So I can immediately, after the first step already, exclude all these nodes here, because I know that all these nodes to the left are going to be smaller than 35. So I'm not going to find 41 in there if it exists. So I'm going to look at the right. So all this here is irrelevant from now on. I've halved the problem size, so to say. Then we can look at 46 and know that if 41 exists, it's not going to be here. So I can ignore all of these. It's going to be to the left. So I'm going to go here, then I'll look at 37, and then I go to 41, and I'm here. I can ignore this one. And it doesn't matter how large the tree gets, we always have the problem size, because we either go left or right, and all the other nodes are irrelevant. We can go left or right, and this action alone halves the problem size. By going right, I ignore all these nodes here. By going left, I would ignore all these nodes here, right? So you're constantly halving the problem size, and because of that, you end up with an average case runtime complexity of log base 2n actually, which is just logarithmic runtime complexity. But we're going to see why this is not the case in the worst case scenario. So let us talk about the basics of the AVL tree. Now AVL is essentially just a combination of the two last names of the founders, of the inventors of the AVL tree, so nothing that has a deeper meaning here. And essentially the AVL tree is based on a so-called balance factor. And this balance factor is calculated by the height of the right subtree minus the height of the left subtree. So this is what the balance factor is. So let's say we have a simple node here, and we have a left child and a right child. Now, if we want to calculate the balance factor for this particular node, what we do is we get the height of the right subtree, which is obviously 1, and then minus the height of the left subtree, which is also 1. So in this case, the balance factor would be 0. So it would give this node a weight of 0. Now, if we have one more node here, we would have height of 1 here, a height of 2 here, so 1 minus 2 is minus 1, and this node would have a balance factor of minus 1. So this is how we calculate the balance factor. If we have 2 here, 1 here, the balance factor would be 1. Now, what we're trying to do here is we want to have each node being balanced, and balanced means that the balance factor is either minus 1, 0, or 1. If we have a difference of 1, of a maximum of 1, we accept it as balanced, but if we have a difference of larger than 1, we don't accept it as balanced anymore. So in this case, it's balanced. In this case, it's also balanced. In this case, it is no longer balanced, at least not the subtree here. But for example, this would also be balanced here. But the moment that we have 2 more childs somewhere like this, is no longer balanced, because first of all, we have a height 3 here and a height 1 here, so we would end up with minus 2, which is not allowed, of course. The absolute value is larger than 1, the difference is larger than 1. But even if we had something like that here, it would not be possible, because yeah, you could say here we have 2 and here we have 3, so the balance factor of this node would be minus 1. But the problem is, if we look at this node here, so this node, the first node, the root node, would be balanced, of course, so this one is balanced, but this one is not balanced, because if you look at it, you have a tree of the height 2 here and height 0 here, so you would end up with minus 2 as well. So we want each node to be balanced, and if not all, if it is not the case that all nodes are balanced, the whole tree is not balanced. So an unbalanced node can happen also somewhere deeper in the tree. You could have a perfectly balanced tree like that. I don't know. So these are actually balanced when you look at the root node, of course. So you can continue on and on forever. And if you compare the two sides here, the heights of the subtrees, you would end up with 4 minus 4, which is 0 and totally balanced. So the root node is balanced, but this node is not balanced because we have 3 and 0. So we would have minus 3, here we would have 3. So the absolute value is larger than 1, and thus these sub trees are not balanced. And for a balanced tree, we want all the individual nodes to be balanced, because why is this the case? Let's say we have, again, this tree that I just plotted here, something like that. Our goal is to end up with a logarithmic runtime complexity. And if only this node is balanced, yes, I'm halving the problem size with my first action, but then I'm ending up with a path and I have linear runtime complexity again. So I want to always roughly halve the problem size with each step. This would be log 2 of n, or big O of log 2 of n, no matter what happens. So this is our goal, and now we're going to take a look at how to do this. Now the question still remains, what are we going to do in order to balance these trees, in order to rebalance these trees? Let's say we find unbalanced trees. What can we do in order to rebalance them, and how can we do that in logarithmic time? Now, in order to answer that question, I have prepared 4 cases here, case A, B, C, and D, that are all unbalanced trees with a balance factor of either -2 or 2. And we're going to look at how to rebalance these because all of those need a different solution, kind of different solution at least. Now, let's look at case A. Case A is a very simple case. We have a -2 balance factor, which means that the left subtree has a height that is 2 larger than the right subtree. So in this case, we have a height of 3 here, and we have a height of 1 here. Thus, we have a balance factor of -2. And the question is now, how can we rebalance that tree so that it still makes sense? It's still a binary search tree, so to say, so we can still have the property that the right child is always larger, the left child is always smaller, and so on. How can we do that? Now, in this case, it's pretty simple. It's just performing a so-called single right rotation. This is called a single right rotation. Single right rotation. A very simple thing that we need to do here. The only thing that we actually do is we rotate so that B becomes the root node and A becomes the right child of B. C remains the right child of A. And then one more thing that we do is we get E, which is the right child of B, and let it be the left child of A. So let me draw the tree once we have done the rotation here. So think about it, we rotate here, so B becomes the actual root node here. I just need to find the colors here, sorry. So we have green and white, there you go. So we have B as a root node, then the right child of B is A, then C remains the right child of A. And now what we did is we said E is going to be the left child of A. Now this makes sense, of course, because think about it, E is obviously larger than B, but less than A. And if we put it to the right side of B, it's still larger than B and less than A. So we can do that without problems. And now the rest remains the same. So we have D here and F here. And this is how you rebalance this kind of tree, because now you have 0, 0, 0, you have -1, you have 0, and you have 0. So this is a perfectly balanced tree. We don't have any major imbalance here, and it's all done with a single right rotation by just rotating that. Now, this is not so simple at case B. We're going to look at that in a second, but now we can look at a very similar case, which is the case C, because here we only do this, we do the same thing, and the only difference is we perform a single left rotation. So single left rotation here, essentially the exact same procedure. Now we let C be the root node, A is the left child of C, D becomes the right child of A. We have the same logic here, so let's draw it out. We have C, C is the root node, then we have A, then we have D becomes the right child of A, because of course D is less than C, but still larger than A, so D is less than C, larger than A. Makes sense. Then we have B, and then we have E and F. And we can see that the balance is the same. We have 0, 0, 0. Here we have 1. Here we have 0 and 0. So case A and C are very similar and can be solved with a single right rotation or with a single left rotation. Now let us look at case B and D. The solution here is quite similar to case A and C, but we need an extra step in order to get there. Now, the first thing we want to do when we look at case B is we want to get it into the same structure that case A has. Why? Because now if I'm going to rotate here, so if I say rotate a single right rotation here, the problem is that I have E and F, and then I have problems because I would end up with a tree that is B, then I would have A, then I would have E, and then I would have F, and then I would have C, and then I would have D here. And the problem is then I'm, again, one more time unbalanced because I have 1 here, then 2 here, 3 here, so I have an unbalanced tree again. I cannot just go ahead and perform a single right rotation. So in order to make an efficient rebalancing on case B here, what I need to do is I need to first perform a single left rotation on the subtree. Even though it's balanced, we don't have any major unbalance here. But what we need to do is we need to rebalance, so to say, or at least it's not really rebalancing because it is balanced, but we're going to perform a single right rotation on B and E. So what we're going to do is we're going to, let me just do this up here. We're going to rotate here so that E becomes the root node of this subtree here, and B becomes the left child of E. So what we end up with is, I'm going to do it without colors now. We have A, and then we have E, and then we have B, and then we have D. Come on. Then we have D, and then we have F here. Or actually, do we have F here? We have, sorry, we don't have F here. We have F here. And then we have C here. And now we can see that this here, even though the letters are not exactly the same, this tree that we have up here after one left rotation is exactly case A. And now we can perform a single right rotation and get the same result that we got with case A. So this is called a double left right rotation. This is what we need to do in case B. We need to first go ahead, take this subtree here, rotate it, perform a single left rotation so that E is the root node, so that we end up with the same structure that we have in case A, and then we just perform another single right rotation on the root node here, so the same thing that we did for case A, and we end up with a rebalanced tree. So what we need to do here is just, again, to go ahead, E is the root node, A is the right child, F is the left child of A, and so on. Actually, the same thing that we did here, nothing too complex. And for case D, it's also not too complicated. Here we do the same thing, but first we rotate right, then we rotate left. So in this case, again, without any colors, A would be still a root node. Now here we would rotate D and C, so we would get D as the node here, then C as the node here, E as the node here, then we would get F here, and then we would get B here. And as you can see, this is the exact same structure that we had in case C, even though the letters differ, but it doesn't matter. And then what we do is we essentially just go ahead and rotate, do a single left rotation here, and we end up with a balanced tree once again. And this is called a double, a double, obviously right left rotation. And this is how you solve all these different scenarios, all these different cases of unbalanced nodes. You're going to have unbalanced subtrees, you're going to have unbalanced tree as a whole, but wherever you find structures like this, you can solve them with single right rotation, single left rotation, double left right rotation, or double right left rotation. Last but not least, let's quickly mention why this is possible in logarithmic time, so why this is in O of log n. Obviously because the rotation itself can be done in constant time, and we will never ever have more rotations than we have levels. No matter what happens, we're never going to rebalance and have more operations, more rotations than we have levels. And the levels are in a balanced tree logarithmic, so whatever we do, whatever we end up with, we cannot rotate more times than there are levels, and the amount of levels is a maximum of logarithm 2 of n, logarithm base 2 of n, in a somewhat balanced tree. This is the case, and because of that, the rebalancing of a slight unbalance in the tree can be done in logarithmic time. And because of that, the rebalancing is done in logarithmic time, inserting into a balanced tree, logarithmic time, deleting from a balanced tree, logarithmic time, finding elements in a balanced tree, logarithmic time. And the moment you delete something or insert something, you might cause an unbalance, but the rebalancing itself is also logarithmic. So whatever we do, it's always going to be logarithmic. So now let us look at this example of a B tree here. We're not going to talk about the formal definitions, the exact formal definitions too much. We're just going to take a look at what a B tree has to B kind of, and then we're going to talk about how to rebalance it, how to insert elements, find elements, and so on. Now, every B tree has a certain order, and this order in this case is 3, so M is the variable for the order. In this case, we have a B tree of order 3, and this means that we can have a maximum of M child nodes. Now, in this case, you can see, of 3 child nodes, sorry. In this case, you can see here we have 3 child nodes. We have, so this thing here is one node, one block, and this one block here can have 3 children as a maximum. But at the same time, it has to have M divided by 2 and the result sealed, so rounded up, child nodes as a minimum. So except for the root node example, for example, the root node has to have a minimum of 2 children. The root node has to have a minimum of 2 children, but all the other nodes, except for the leaf nodes, of course, have to have a minimum of M divided by 2 and the result sealed child nodes. In this case, 3 divided by 2 is 1.5 and 1.5 sealed is 2. So we'd have a minimum of 2 child nodes. What does that mean? This means that if we are below the minimum or above the maximum, we have to open up a new level, we have to reshift values, we have to rebalance the tree, adjust the structures so that we can fulfill this property. Also, the amount of child nodes has always to be larger than the amount of keys. So if I have 2 keys here, I have 3 child nodes. If I have 1 key, I have 2 child nodes. If I would have a B tree of order 6 or something and I have 5 keys, I would have to have 6 child nodes and so on. So this is another rule that has to be fulfilled when we're talking about B trees. And one rule that's also very important is all the leaf nodes are at the same level. The leaf nodes are at the same level, which means that we cannot have a bunch of them here and then, it doesn't make sense anyway now, but I cannot just go ahead and open up this here as a new level and then I have some leaf trees here, leaf nodes here, and then some leaf nodes here. All the leaf nodes have to be at the same height, at the same level. And those are basically the criteria for a B tree. And once these criteria, or as soon as these criteria are not fulfilled anymore, we need to rebalance, restructure, and do something about it. So let's go ahead and try to insert a new element and unbalance the tree or violate these criteria to see what happens. Now let me just delete this real quick. And what we're trying to do now is we're going to add the element 80 to the B tree and see what happens and see how we can rebalance it. Now, if we want to add the element 80, I go to the root node, it's 25, so I need to go to the right. Then we have 37, 45, 80 is larger than 37, so we're not going to the left. It's also not in between 37 and 45, because then we would have to go down here. That's not the case, but it's larger than 45, so we need to go to the right. And then we have those 2 keys here. So we have 67, 77, and actually would have to go to the right, but since we're at the leaf level, we just append it here into the same block and see what happens. Now the problem is that we have a block of 3 with 3 keys, which is not allowed because we have the order 3, which means that the maximum amount of keys is 2 because the child nodes has always have to be larger than the keys, and the keys cannot be larger than 2 if the child nodes have a maximum of 3 or are a maximum of 3. So what we need to do now is we need to adjust. So what we do is we shift up the center value one level, shift it up one level, yes. So what we do is we essentially say by 77 and we shift it up into this level here. So actually let me just delete a bunch of things here so that it doesn't look too messy. We just delete this. So actually 77 is removed from this leaf level here. And what we would do next is, I'm also going to delete the 80 here and rewrite it. So now we have 80 down here and we have 77 up here. But now we have the same problem here because here we also have 3 keys. And of course, what I could do is I could say, okay, then we have 80 because obviously we need to do it like that or something. But that doesn't make sense because we're not going to leave 77 here because we have a B tree of order 3. So what we do here next is we shift up the center value again. And what happens then is we shift up 45 into the root node. And then essentially what happens is we remove it and we essentially replace it by 77. We replace the position by 77 or with 77. and I'm not sure what number it was, 45. I think it was 45. And then we end up with this here. And because we end up with this here, we have 2 keys and 3 child nodes. We cannot just have 2 child nodes and 2 keys. We need to say the middle points to 37 and the right points to 77. So let me maybe again clear this up a little bit here so that we don't have it too messy. We're just going to delete these red arrows here and redraw the 45. So what we would do is we would say, okay, these are now separate blocks. So again, we're going to split them like that. And we have 37 here and 77 here. And then we connect those two. And then we say, okay, to the right you have 80, to the right, to the left you have 67. So essentially you also split these 2 nodes here. Come on, don't do any dumb shit here. We have 80 here and 67 to the left. It's not the most beautiful tree that you can draw, but that's essentially what you do when you enter an element and the structure violates the criteria. You shift up the center element because we had 3 keys at the leaf level, so we shifted up the center key. Then we had 3 keys at one level above that. We had to shift the center key again, and now everything's fine because we have 2 keys. That's okay in a B tree of order 3. We have a balanced structure here. We can find elements in logarithmic runtime complexity. It's not a problem. And all these criteria are still satisfied and met. Remember, we had the leaf nodes, same level. Leaf nodes had to be at the same level. And all this criteria here is satisfied, so the B tree is rebalanced. Now let's look at what happens when we delete elements and violate the criteria. What happens then is, it depends on what kind of deletion you perform, because in B trees you have many different scenarios for insertion and deletion. My recommendation to you is if you want to get a basic understanding of what's happening, or not a basic, but a deep understanding of what's happening, I would recommend going online and typing B tree simulator into Google or DuckDuckGo, whatever, and play around with it a little bit, because reading the formal definitions, you can learn it, you can memorize everything, but I think you'll get more of an intuition by playing around with a simulator, with a visualization tool. You can also additionally go to a textbook and read all these definitions there, but I think they're going to confuse you more than just playing around with the simulator. But essentially, if you delete a leaf node, what happens is you essentially just rotate so that the missing place gets filled up. So in this case, if we delete 22, for example, what would happen is we would, of course, delete 22. And then the obvious thing to do here is you just have to rotate so that 15 ends up at that position here. And you shift 11, so you shift 11 up here and 15 down here. And you'll rotate basically in a similar way to the AVL tree rotation, so that you end up with 4 at the left side and 15 on the right side, and in general it's 11 up here. So that's a single rotation, a very simple rotation if we delete if you delete a leaf node. Now what happens when we delete a node in between and a level in between? This is a little bit more complicated, but it's still very similar to the AVL rotation. So if we delete 15, for example, what happens now is we rotate the whole tree. So we say this is a rotation here. And what happens is we have 25 here now. And we replace 25 by 37. But then we need an additional, so we say 37. But then, of course, we need an additional rotation here, because now we have this node here removed, and we have only 1 key at this level on the right side. And because of that, of course, we cannot have 3 children here, but it would also not be correct to just take 35 and put it into the same block as 43, because 35 is actually less than 37 and cannot be on the right side. So what we do is we actually combine these 2 blocks here. So actually 35 and 22 are combined. So 35 and 22 are combined, and that's how you rebalance the tree in an AVL-like way. So you essentially just rotate the way that you need to rotate in order to fill up the empty slots, and then you make sure that the individual elements are on the right side. Like not on the right side, but on the correct side. And as I said, if you want to get a real good feeling about this, a really good intuition about this, I would recommend playing around with a visualization tool. There are a lot of visualization tools for B trees online because, as I said, I don't see a lot of value in reading the exact definitions unless you want to program an algorithm with it or something like that. But in order to understand what B trees actually does and how they balance them, rebalance themselves and so on, I think it's enough to just play around with the simulation tool. Now, last but not least, we're going to talk about why this is possible in logarithmic time again. Obviously, because the rotations, in the same way that it was true for the AVL trees, we're not going to have more rotations than there are levels, or at least not significantly more. So we'll end up with logarithmic runtime complexity. And also, when we add elements, we need to shift up, shift up, shift up, and so on. But we cannot shift up more times than there are levels, because then, of course, we would be above the root node, and this doesn't make sense. So all these operations, finding elements, adding elements, inserting elements, removing elements, or rebalancing the tree, everything is possible in logarithmic time. But B trees have the additional advantage that we have data saved in blocks, and because we have more data in one node, in one block, we have less many times. We need to access less many times. And this is very beneficial when it comes to external storage media with a block-like structure or block-oriented structure. So last but not least, we're going to talk about B star trees, which are a little bit special because all the nodes in between here, all the values in between here are just used for navigation. Now the B star tree has the property that all its elements, all its actual values that we're interested in are leaf nodes. We don't have any value that we're interested in that is not a leaf node. All these values here are just values that are guiding us, that are navigating us towards these values that we're actually interested in. So 3, 8, 14, 27 are just values to tell us you need to go left, you need to go right, you need to go to the center, and so on. They're not values themselves that we're interested in. Now, this is essentially what a B star tree is. And this number here, the value of the navigation key, is always the largest element of its left child. So in this case, you have 3 because 3 is the largest element of its left child tree. The actual element, we're not talking about navigation elements. 5 is 5 because it's the largest element of this left subtree. 8 is 8 because it's the largest element of the left subtree. 14 is 14 because it's the largest element of its left subtree. 18 because 18, left subtree. 27 because 27, and so on. So it's always like that, and this is the pattern here. We always have these in-between layers in order to navigate, and the amount of elements that we can store at the leaf level is determined by a so-called K star parameter. And this K star parameter, let's say it's 2 in this case, means that we can have from K star up until 2K star elements at the leaf level. So you can have a minimum of 2 or a maximum of 4. So 2, 3, or 4 elements at the last leaf level. You cannot have less than those. You cannot have more than those, because if you have more or less, we're going to restructure the whole tree. We're going to add an additional level, or we're going to remove a level and restructure everything so that it still fulfills this criteria. Notice, however, that this parameter here is different from the M parameter, from the order of the tree. The order of the tree is still 3 here, so it's an ordinary B tree, but we have the property that in the leaf level we can store 2 to 4 elements per node. So this is essentially what a B tree is, a B star tree is. A B tree where we have essentially all the layers in between are just used for navigation, and all the actual data is stored at the last level, at the leaf node level.